So it looks like we are live. Yeah, we are live. Hello, everybody.
Hi.
Hello.
So today we are going to have a very, let's say, unusual hangout. I've got two very dear guests here, Reds Rhetoric and Anthony. And I really don't have the feeling that I, at this point, really don't have to say much about all that stuff because I think the conversation will start immediately.
Sure.
So,
I don't mind opening if you want.
Sure, if you like.
Okay. A few weeks ago, Hector and I were talking about the pendulum, and we were working out, does it actually do what it says by science that it does? And previously to Reds getting involved, we discussed whether we should repeat the experiment ourselves to see whether or not it did what they said it did. And about a week later, which was 2 or 3 days ago, Alex sent me a message saying, hey, Sean Hufford's having a live hangout against Jeren. You might want to listen, but I was in bed, so I missed it. And whilst I was skimming through some of the content, I heard our friends outburst in the middle of it, and I thought, ooh, that's got to be worth debating because a lot of that stuff that was said in there needs to be addressed. So I addressed it with the video that you saw recently, and here we are. Essentially, we realized that well, I was watching the gyroscope experiments recently from a guy, I can't remember who showed it all. But basically, he spun a gyroscope and stuck it on a 24-hour clock mechanism, which demonstrated the 15 degrees precession. And it was quite accurate. In fact, it was accurate as to the 15 degrees in an hour. And when you conclude that the gyroscopes are capable of demonstrating the 15 degrees precession in an hour, it means that then you can challenge the questionability of Foucault's pendulum from a scientific viewpoint. Essentially, the issue that I had was that Eric Dubay had said numerous things in his video. I'll post his video in chat so you can, let me just get to it. I'll have to find it. So basically, he said some things, and I'll quote some of the things he said, which is the authority for challenging to see whether or not the pendulum does what they say it actually does. One of the things he says is, the truth is, however, Foucault's pendulum is a failed experiment which proves nothing but how easy it is for pseudoscience to deceive the malleable masses. So this is one of the things that I thought, let's check it. So speaking with Hector, we agreed that we were going to do the experiment. Another thing he says in the video, Alex, if you could find that video that he's got. In fact, I'll have it here. Let me just dig it out. It'll be in my history. Where is it? There we go. I'll just post this in chat so that people can see it, so that they know which one I'm referring to. There we go. Paste. That's the link for the video that gives me the authority to challenge the Foucault's pendulum. Another thing he says, quote, since it has been found that, as often as not, the pendulum went round the wrong way for the rotation theory. And then he says the word chirogram, I don't know what that means, has taken place of exaltation, and we have proof of the failure of astronomers and their efforts to substantiate their theory. Then he also says, quote, sometimes they rotate clockwise, sometimes counterclockwise, sometimes they fail to rotate, and sometimes they rotate far too much. Another quote he says is, scientists who have repeated variations of the experiment have conceded time and time again that it was, quote, difficult to avoid giving the pendulum some slight lateral bias at starting. The behavior of the pendulum actually depends on 1, the initial force beginning at swing, and 2, the ball and socket joint used, which most readily facilitates circular motion over any other. The supposed rotation of the Earth is completely inconsequential to the pendulum swing. If the alleged constant rotation of the Earth affected pendulums in any way, there should be no need to start pendulums in motion. So these are the quotes, and this is the reason why I was challenging it. And it was built on the back of the gyroscopic observations that are demonstrated. And that's essentially the reason for why we're doing the experiment. The reason Reds got dragged in is because of the video that his outburst on Sean Hufford's video. But ultimately, Reds is an avid ball earther, and he can. I'm sure he's the right guy that can add to this experiment. Effectively, what that would mean is that there's somebody in Florida, somebody in Germany, somebody in England at different longitudes on the Earth that will be able to verify or prove that the science doesn't do what it says it should do. And obviously we have a ball earther on the one side, we have a physicist in Germany in the middle, and we have myself that's challenging the evidence of the spinning ball. So between the three of us, we should be able to at least verify whether or not pendulums do what they tell us that they should be doing. But it may be the case that they don't do what they tell us that they should be doing. Or it may be the case that there is no rotation of the Earth and they do what they say they should do. Either way, the pendulum experiment will either confirm the science, or it'll confirm the science but show there's no rotation of the Earth, or it'll do absolutely nothing at all. We'll get random results. So that's the reason why we're here today. And we're here essentially to discuss how we're going to do what we're planning on doing, what the basic rules are, how we're going to observe, how we're going to report it and document it, and how we're going to actually. One of the key things we're going to be dealing with is how are we going to, if one of us does the experiment first, do we tell the other two of the results that we've achieved, or do we keep that quiet until the very end, and then anything else that other people can think about along the way that may fine-tune the experiment for the benefit of everybody? But essentially, we're challenging Dubé's video on the Foucault's pendulum on the back of the gyroscopic tests that prove that there is no rotation of the Earth. And we're essentially checking that particular fact. So I guess we could hand back to Alex and take it from there.
So one thing I'd like to address just before we start, the gyroscopic video you referred to, there's two things I'd like to mention before we go any deeper. First, when this guy contacted the manufacturer of the gyroscope, the manufacturer himself said, no, our gyroscopes aren't accurate enough to measure that. And secondly, we had a lengthy discussions about possible errors that might have happened both while he was trying to measure the rotation of the Earth and checking with the 24-hour clock mechanism. We're not going to get into detail of that, but I just wanted to tell you, if we manage to measure a rotation of the Earth, it's a lot more reasonable to say that there was something wrong with the gyroscope experiment than with the Foucault pendulum.
Let me address that. Let me address them 2 points. The recent gyroscopic experiments show that when it's placed on the clockwork mechanism at 15 degrees in an hour is not only demonstrably accurate, it does it each time he does it. So it seems to be not only precise, it seems to be reliable. So the issue is, and when the second point, the manufacturers say it's not precise enough, well, it evidentially is by all accounts. And if they say that they didn't test for
with the cable being rather stiff and probably holding the gyroscope in place while the clockwork mechanism rotated around it, we've been through that already.
He has addressed that in his video. He said that he's done the experiment again and it didn't move, and I accept that. He did say he was going to upload a video, and I haven't seen his upload video yet, but he did say that he's redone the experiment without the wire in the way, and it does the exact same thing. It does nothing.
Okay, in that sense, in that case, I would really like to see the video, but before I see that video, I'm still going to be skeptical.
But with regard to the second point, he said that that even the manufacturers say that it isn't sensitive enough to record the rotation of the Earth. Well, that suggests that it's because they tried to measure the rotation of the Earth and it doesn't appear to do it. So that's why they said it. Doesn't mean it can't do it, because it appears that it can do it.
Or it's not accurate enough to do it. Anyway, that's basically why we're here. So let's move on from that.
Basically why we're here. So really, the challenge is: does Foucault's pendulum verify up or not? And according to Dubé, it swings clockwise, sometimes counterclockwise. Sometimes they fail to rotate, and sometimes they rotate far too much. So essentially, that is essentially what we're doing.
Yeah.
I mean, Reds, do you want to speak?
Yeah, you're saying that we're all here to do this thing. When did I agree to do this again? Quick question.
No, you agreed to do the hangout first.
Yeah,
so
I agreed to do the hangout, but when did I agree to do this pendulum thing?
Well, I was led to understand, I was led to believe that you did want to do it and that you wanted to run things by us before we started. So if it's a I mean, do you want to do it or do you not want to do it?
No, that's not why I'm here. I'm here to simply call you out for just being butthurt because you made a 35-minute long reply to something that had absolutely nothing to do with this pendulum.
Well, in that case, why are you even here? We're not even here to discuss the reaction to the video. We're here to discuss the experiment and the parameters of it. So if you're not here for that, then you may as well just leave.
Or I can simply get some answers from you before I leave, because this is my 3 o'clock in the morning and I woke up to actually get some answers from you. So what seems to be the case between you and me? Because I haven't actually mentioned your name in like at all. And on top of that, your little reply or this little thing has absolutely nothing to do with me to even begin with. I never mentioned you in the video that you decided to make, yet you decided to get butthurt and make a 35-minute long rant video over something that had something to do with pedophilia and people saying that people who use science are guilty of pedophilia. So tell me, how do the two connect?
Reds, that's a discussion that we have a different day. We're here to talk about the pendulum and the experiment itself. If you're not interested, leave.
No, I'm not going to leave. I'm going to get an answer. That's the reason I was here, and that's what I told Gio when I came in here. And so if you were misinformed, I'm sorry, but I'm here for the right reasons, to get some answers. Now, if you're not willing to provide me with those answers, I'm simply going to assume you don't have those answers, mainly because you're pulling stuff out of your ass, as you always do, and then I'll simply go back to bed, because that honestly sounds really fucking nice right about now.
Reds, watch the video. I've explained my position with you in full in that video. If you don't understand it, then there's not a lot else I can do other than repeat myself. The reality is you misrepresented me, then deleted the video so I couldn't respond to you, and then used that as the nomination for the Dickhead of the Year award. What fucking planet are you on? It's got
no, dude, it's not called the Dickhead of the Year award. Okay, get your shit together. It's called the Dumb Fuck of the Year, which, by the way, you came in dead last. That's how little you matter. When it
maybe that means I'm more credible than the others.
Or it means you simply no one gives a fuck about you. When it comes,
so why are you even here then? If you're not here to benefit the experiment and do stuff to do with pendulums, piss off.
Well, I'm sorry that you think that that's what this was about, but I'm sorry, it isn't. So
yeah, Red, actually, it was supposed to be about the experiment.
Yeah, it was supposed to be about that, but that's not what we discussed, Gio.
Alex, do you want to tell Reds? Do you want to tell Reds what my prediction was?
Which one? Regarding the experiment itself, or your Red's reaction to it?
I gave 2 parameters to what Reds would do.
Give me a second.
Yeah, that I would reply and call you out for being butthurt.
You're not calling me out. You're being a dick.
Yeah, I am. Yeah, I am.
He meaning you would either not do the test, not get the results you want, and find a reason to excuse yourself, or do the test but invent circumstances to explain why you wouldn't get the results. Or
just read number 1.
Which one?
Just read the first one again.
Do the test, not get the results he wants, and find the reason to excuse himself.
Oh, was that the first one? Basically, I said that you wouldn't even do it at all, and that appears to be the position. Are you going to do this, or are you not going to do this?
I never agreed to it, and it's already been done. Just because you don't understand the pendulum doesn't mean that I need to do it again and then have you completely disregard the results once again.
Right. If you're not going to do it, Reds, piss off. You're wasting my time. You're wasting your own. You could be in bed.
Yeah, I could be in bed, but at this point I'm up already. So I need to know this. If you're going to tell me that you made a 35-minute long video, you expect me to sit through 35 minutes of bullshit? You really expect me to sit through that when you could simply tell me right now what the hell pedophilia and people saying that people who use science are guilty of pedophilia has anything to do with a freaking pendulum?
Why is pedophilia anything to do with anything?
Because that was the gist of my rant on Sean Huffert's channel, you dumb
fuck.
It
wasn't. No, it wasn't.
Did you even watch the fucking video before making your reply?
Reds, go back to the video I made. I went through it point by point.
Absolutely not. Let me make this very clear. I'm not going to sit through any of your videos. You made a reply to my original video, which had something to do with the power station, that was almost 2 hours long. Not dealing with it.
Step the fuck out. Say what you got to say and leave, because I'm not even talking to you. We're here to talk.
Don't talk to me, because you can't answer for yourself. You can't answer for yourself, as you always have.
Myself and just listen to you. This is freaking hilarious.
Hector, I'm glad I could be entertaining. Grab some popcorn. It's going to be awesome. When you have this guy make a reply, it's literally off the top, as in, just like with Jism, just like with all these other people, he can't keep it concise and to the point. He can't just say what he has to say. And then when you ask him to justify it, he runs away like he did there. So I guess he was the one pissing off, not me. So no, when I came here, I never agreed to do a pendulum test. I never had any intention of doing a pendulum test. And even if we were to do a pendulum test, he would not understand it. He would not get it. He would find some way to deny it, just like he's denying ships disappearing over the horizon, or the fact that half of the power station that I'm looking at has disappeared under it. This guy doesn't even believe the Earth is round, let alone that it's spinning. And so, hell, you know, what's the consequence of that? The consequence of that is that we are literally all wasting our time with this douchebag. He will literally make a rant or a video replying to something about a pendulum and whether or not the Earth is spinning or not, when my rant was about people that say that people of science are guilty of pedophilia. This is the type of shit that Jism was saying in this video, and that's what I was replying to. And yet this guy wants to say, oh, it's somehow connected, but I'm not going to tell you how. You have to watch my 35, almost 40-minute long video to find out. Fuck off, dude.
To be completely honest, I watched it, and I didn't see anything where he connected it to your rant.
So essentially, he would have wasted 40 minutes of my life that I was never going to get back when I could have been doing other shit. Interesting. So, you know, and this is exactly what it is with him. And this is exactly why I ignore the guy. He does not matter because he does not make coherent points. When he wants to have a conversation, or if ever, if we ever wants to have a conversation, he's going to hop, skip, and jump between topics like a raccoon that is fucking high on meth. He is going to do whatever would be considered crazy in terms of topics. Oh, let's jump to pedophilia. Let's jump to the pendulum. Let's jump to actually measuring how round the Earth is. It's crazy.
Yeah, that's an issue.
Have you guys noticed that? He kind of jumps around.
Yeah, and he just left.
Yeah, I know he just left because I wasn't going to agree to his bullshit. And other than that, this is not his hangout to control. So when I got in here, I let him know. And Gio, just to be clear, in the little conversation that you and I were having on Skype while I was at work, did I or did I not agree to this pendulum thing?
You agreed to do the hangout, not the pendulum test itself.
Thank you. Okay, and did I or did I not agree to talk only about the pendulum, or did I say I was simply going in there to ram his bullshit right up his ass?
You said the latter one.
Thank you. Okay, so essentially everyone knew. So Anthony, if you want to blame somebody, blame Gio. Sorry, Gio, but thank you. I'm not throwing you under the bus or anything. Thanks for that, by the way.
No
and
problem.
So with all that being said, Anthony, being that Hector actually already viewed your video, and since he appears to be a guy that knows his shit, he can't see where you connected it. So when you're ready to justify that connection, get back with me. But until then, piss off. Can I go to bed now?
Sure.
Thank you.
Well, that escalated quickly.
That was weird. That always happens when the two talk. But I still want to do the experiment, to be honest. So I just messaged Anthony if he wants to rejoin so we can talk the parameters about it. If you like.
Sure.
So let's give him some seconds. By the way, when he was talking, Anthony, I was dropping out for 30 or 40 seconds because for some reason my Google Hangouts doesn't like me.
Yeah, things happen.
Hello.
I'm not prepared to
that
talk
is
with Reds about
quickly.
bitching.
Yeah, that was really weird.
Right.
Just to clear that up, when you offered him to, when I told him that you would like to do the experiment and you invited him to do the experiment as well, he confirmed that he would like to have Hangout first, which is the one we're currently having. So he didn't agree to do the experiment before at least
honest, I didn't expect he would. I didn't think he would. I don't think that he will do anything to. He said in his video that I was quoting. By the way, Hector, have you actually watched the video? I quoted all of the parts. Like, I played the parts that I was addressing. I went over the paedophilia comment and didn't address it at all because it's an irrelevant part of his video. His video was that he's done all the shit that flat earthers have asked him to do. He's bored all the cameras. It's bullshit. The reality is, when he's put onto the point, he ain't going to do shit. That's the reason why I got him involved. If he's not on this hangout to talk about pendulums and what we're planning on doing, he can fuck off, because that's not what we're not here to have a clusterfuck. We're here to address pendulums and nothing more. So with regards
in that case, let's skip all the things about your video and any kind of cluster, any kind of thing that could start one of those famous clusterfucks, and just get to the pendulum.
Yeah. But with regard to you, Hector, you've misquoted, because if you've actually seen that video, you will see that I directly addressed his points that he made in that rant, and you've misrepresented me again about something that I didn't do. I didn't ignore. I directly connected them all. So you've either not seen it or you've misrepresented me, and you deserve to either stand your ground and say, yeah, that your comment is correct and that I didn't do what I clearly did, or admit that you haven't watched the film and therefore you're talking out your ass. So ultimately, I haven't done anything.
Once I didn't see any connection to a pendulum, which is what I told Reds, and in regards to all the other points, I'm just gonna watch it again, because it's been quite a while since I watched it last time. But I'm not going to watch it right now, because today we're talking about pendulums.
We are.
Okay.
But I'm pissed off
about the pendulums.
Hang on.
Yeah.
Hector,
Sure.
I'm pissed off that you've misrepresented me again, because I did address everything in his rant. I addressed it directly, and you've either not seen it or you're mistaken. Either way, I deserve that comment that you made to be corrected, because it's wrong. I addressed everything he said. Right, let's move on. You can do that at a later date, Hector, but it's a bad mark because you misrepresented me again. Second time we've done that, by the way, Hector.
Okay, can we finally talk about pendulums?
Yes.
Okay, great.
Right,
Do you guys all understand the physics behind it?
We'll consider Reds out, because I didn't think you were going to do it anyway. But at this point, it's just me, you, and Hector, okay?
Yeah, sure.
Do we understand the physics?
Depends on how much of the physics you want to understand for that, because there's a little more to it than it seems at the first time. In particular, if you've got a pendulum that's not that long, or you're moving it by more than, let's say, 10 or 15 degrees, you get effects of something called nonlinear systems. That's due to the pendulum not being a strict harmonic oscillator, only in a small angle approximation. And as soon as you get into the nonlinear part of physics, basically a lot of weird shit starts to happen.
Yeah, I think we can go for the usual case, long pendulum, no big amplitude of the movement.
So essentially what you're actually saying is, in the period that is considered generally the middle 75% of the swing of the pendulum, it creates its own torque, which stops out for outside effects affecting it. And then the only issue really is the point that we've been discussing, which is what happens at the extremity of each swing. Does it maintain that? What
I'm referring to is pendulum angles higher than 10 degrees to the outside. And what's happening there isn't just that forces that are otherwise very small get an impact on the overall pendulum that's massive. It's just that the pendulum itself cannot be approximated as a harmonic oscillator in that range, which means we're getting a massive amount of weird shit happening, as I just said. And where the hell is my pen?
So
basically, the bigger the swinging movement becomes in a horizontal way, the less accurate the model becomes that we usually use.
So essentially, you agree then with Dubé's statement, which is, quote, since it has been found that as often as not, the pendulum went round the wrong way for the rotation theory.
No, that's something different.
What about this then? Sometimes they rotate clockwise and sometimes they rotate counterclockwise.
Yeah, this doesn't have
possible explanations.
Stop, Hector. First of all, this would work without any rotation. The linear approximation that we have regarding the pendulum is just about the time it takes for one swing to be done completely. That is independent of the rotation of the system that it's standing on.
Right.
But the thing is,
we need to talk about pendulum physics a little. Do you agree?
All right. Camera on, pen and paper out.
Sure.
All right.
The only thing you've said so far that I agree with is that it is showing an oscillation rather than a swing.
That's
I think
both
the same.
are effectively the same.
Well,
all right.
What's the difference between the two?
All right. Let's start talking a little bit about oscillations then, because oscillations and frequencies in physics are about as the same as you can be. Usually, let's start with a simplified version of the pendulum swing, where we not have a movement in two directions, but only in one direction, which would be a system like this, where we've got a spring and a weight attached to it. Let's say for a moment that this weight is on a rail and can only move left and right, and the rail is lubricated enough so that any friction in there doesn't really make any difference. In that sense, we have only one force acting onto that weight, and that's the force due to the spring being pulled one way or the another, which I'm going to call the spring force. Let's say from here in either that direction, direction 1 or direction 2. Now, that spring force is usually and let's say we take a x scale in meters, where this is our 0 point. Here's 1, 2, -1, -2. Now, the force that this spring that this spring uses to affect the pendulum is Fs equals minus the position of the pendulum times a spring
Hector, I'm afraid
constant.
you have to write a little bit larger. We literally can't see much of it. Just double it in size. The compression of the Google Hangouts is horrible. Ah, that's much better.
All right. Now, in that case, it's basically what I'm explaining here is how a standard harmonic oscillator works, and then where the issue is with approximating our pendulum as an harmonic oscillator. So, in that sense, our mass of the pendulum here, just going to have mass m, is accelerated in the following way. Basically, it's Newton's first law, basic acceleration. So the acceleration equals the spring force divided by the mass of our pendulum equals minus x times the spring constant divided by mass. Now, if you've ever heard of it, the acceleration of something is the second derivative of its location after the time. In that case, we have to use an ansatz for the solution. In that case, I'm going to use the complex exponential function of e I omega t for as a possible solution. And what we're interested in is the frequency of the pendulum, omega. The second derivative of our x of t, d square x of dt square, equals minus omega squared e to the power of I omega t, and x of t equals e to the power of I omega t. Now, put that into the formula. Omega squared e to the power of I omega t equals, oh, hold on, we need a minus here because I've got a minus here. Forgot that for a second. So we've got our spring constant divided by mass times our x, which is e to the power of I omega t. That minus crosses out, the e to the power of I omega t crosses out. So what's remaining is omega square, which means that what remains is omega square equals the spring constant divided by the mass of the pendulum. All right. One thing that we had to assume for this is that basically that the force that's pulling on to our pendulum is the location of the pendulum times a constant. So basically that it's a linear force. And the thing is, when we're talking about a pendulum, then we only have a semi-linear force in a small range of our pendulum. So basically, instead of instead of our
Spring pendulum.
spring pendulum, but instead of a spring pendulum, we have a string pendulum with our mass here and an angle alpha. Then then basically the force that's accelerating the pendulum is in that direction. So we've got.
Actually, the force that's accelerating the pendulum would be vertical, wouldn't it?
That's basically what I'm doing here is that's the total force applied to the pendulum.
Sure.
But the string is but in that case we have to split up the force into two components, one parallel to the string and one rectangular to the string. This force here, the one parallel to the string, will be counteracted by the string, or else the mass would be accelerated away from the point that it's located at or towards it. So the part of the force that is actually accelerating our pendulum is the one down here. So this is the accelerating force. And the problem, so our accelerating force equals the sine of the angle alpha times times gravity. Now, the thing is, that is not strictly linear. If I may shortly draw a sine curve, however, for a short period of time, let's just draw it here. That's about how a sine curve looks like. It's kind of curved in here, but and it's also going on this way. If I draw a straight line through here, then for this area here, both the sine curve and the straight line are extremely close together to the point where you nearly can't tell them apart. And in that range, we can use something that's called the small angle approximation, where the sine of alpha is about equal to alpha for small values of alpha in here. The problem is, as we exceed that range and we get somewhere in here, we the sine the connection between the accelerating force and our angle isn't linear anymore. In that case, we get terms of third and fifth order due to the sine. And in that case, we don't have a harmonic oscillator anymore, which is what, in other words, as we've got terms of third and fifth order and not only of first order, we have something that's called a non-linear system. And now we actually have to go to different, basically, axes of swing of our pendulum. So basically, if let's say we're now looking at it top down, this is the point where we've suspended our pendulum from, and this is where our pendulum is at. We can have our pendulum, we can have, basically what you can do is you can look at for a perfectly linear system, you could take a look at any swing of the pendulum in this direction and any swing of the pendulum in that direction, so up, down, left, right, individually, and then add the results to add both solutions together to get another function. That's a key property of linear system. If A is a solution and B is a solution to the system, then A plus B is also a solution to the system. The problem is now our pendulum is starting to become nonlinear. So, which means that both of these solutions, in essence, have different frequencies. So, for example, if our pendulum were to swing from here to here and back, I think that's correct. yes, I draw that as a finer line, then the swing in this direction would have a different frequency than a swing in this direction. So instead of continuing to swing this way, at some point, our pendulum will turn this swing into a swing that's got an ellipsoidal path.
Yeah, I agree.
And the thing with that is, in order to stay in the range of our pendulum, where we can still correctly use that approximation for small angles, we have to have the string of the pendulum be very long. I don't know how long the string for you is going to be, Anthony, but I think as soon as you're over 11 meters, you should not see any ellipsoidal path within at least probably 1 hour, but I'm only going to give you a guarantee for about half an hour just to be sure.
All right, well, let me just respond.
That's a lot of math that I have to do by myself. Now I'm going to go to the part where people are saying.
Let him give some time. Let him give some time to respond. Okay.
Hector, while you've got your screen on, this is on a webcam, isn't it? What I could do with doing is either sharing my screen or sharing Hector's screen or whatever. But there's a link in chat that I want someone to play. How's the best way to do it?
Do you have any possibility to record the audio of the video if it would be showing?
It's just a photo. I can do a screenshot. Let me
it's not a problem. I can share it as well.
All right, I'll do a screenshot and I'll share it in chat. All you got to do is open the image.
Okay, sure.
When you were talking about elliptical orbits, is that the way you described it? How did you describe it? At some point, it would go. What did you say?
An elliptical path on an elliptical path.
If you look at the image, that hopefully, oh no, it won't let me share it into chat. All right, Alex, I'll send it to you on Skype.
Okay.
How do we get that on screen?
I have to share it. Give me a second.
Because bear in mind the image that you've just drawn, that that oblate spheroid.
The ellipsoidal path.
Ellipsoidal path. That's the word used. Is that demonstrated by this experiment here, where they've got ink, they've got a well of ink, and they've got the pendulum making the rotations? Do we see that in there, or do we not see that? Because I would suggest we don't see it.
No, we don't see that in there because, as I just said, this only happens when we've got a nonlinear and effectively significantly nonlinear system. If we are still in the basically range of the pendulum where we can basically make this approximation that in the range where we are at, we can't really tell the sine curve and the straight line apart. Then we basically how much of an ellipse we're going to see. So whether we're going to see something like that or just something that looks like this. So a very flat ellipse. Basically, the width of this ellipse gets stronger the further away that straight line here gets from the sine curve.
Do you agree that that's not demonstrated on the picture that's on screen?
Actually, that fits perfectly. That pendulum seems to have a very large line, and the larger the line is, the less of an ellipse you'll get, or basically the slower the thinner your ellipse is going to be. And you see a tiny little bit of that in the video that you've just sent, because right in the middle you don't only see one single path, but you see the path kind of broaden out.
No, you don't.
Hold on a second.
What makes you what makes you interpret that? That is not what you see. You see straight lines.
Basically,
you don't see any curve.
What you'd expect in that video would be a straight line here, and from the beginning a straight line at the end, and basically paint all in between the two, right?
Yeah, but you're saying,
and you'd see in the middle here, you'd expect them to go through the exact same point ever again. This point here should be just as wide as the line you're drawing, right?
Well, not really, no, because you're going to be attacking it at different angles.
Yeah, but this is the 0 point. Every time your pendulum goes through the middle, it's going to go through that point.
So what you're saying is it should be a compass hole rather than a band. You're saying it should be a compass prick mark rather than a band, because we see a band in the picture, but we don't see a band. You're saying it shouldn't be a band.
Hold on.
I
In
don't
the
agree.
picture, basically, the line that the guy's drawing is about as line as my pen line here, with basically the brush in the video is about as wide as my pen line here. But what he's getting as basically the dot in the middle is about this wide.
All right, so redraw. Let's draw that.
So
what
in
just
essence,
drawn.
what I think he's getting is he started out with a straight line, but in the end, he's got a very flat ellipsoidal path.
That's not consistent
Like
with the picture. It's not consistent with the picture, though.
It is.
No, I disagree. Why do you interpret that? Am I misinterpreting that picture that I've just sent you, or are you misinterpreting what you think it shows? One of us is wrong. Just put the picture back up, Alex.
Give me a second.
I mean, the angle there that you've illustrated there is probably... I mean, he's showing that over maybe, what, 5 degrees?
7.89 degrees and about 40 minutes.
Well, to be fair, it's halfway through, so it's not 7.9 at that point. It's about 5 to 6 degrees, I would say. But in any event, let's go with 7. If you reproduce 7 degrees on your piece of paper, your line there, you're going to get exactly what that shows there. You're going to get a band in the middle where it's showing that, and it's not going to be a compass mark. It'll be a band.
Hold on. Line. And 7 degrees.
Yeah. Now, zoom in. If you were able to expand that and make that look bigger, can you see the band in the middle?
Hold on. Camera zoom. It seems I can't zoom in any further.
It's okay, but can you see that if you were to pass and repass that area over and over and over again, what creates the width that you say is there in the... If you go back to the picture now, Alex. What creates that thicker band in the middle rather than the pinhole that you're suggesting isn't what you're saying scientifically. It's to do with what happens with the pendulum when it's at the maximum swing and then it begins its journey back again. That's the problem.
That's a side effect of the Coriolis force. That's creating the total twist of the pendulum.
How do you know that?
That's a mathematical problem that I've got yet to go through, because, as I said, as soon as we're getting into the region of nonlinear physics, things start to get ugly.
So you believe it's the effect of Coriolis, and you don't believe where's the...
A combination of Coriolis force and nonlinear physics.
I'd suggest it's nothing to do with the Coriolis force whatsoever, and I want you to address this particular bit. Let me just get back up to the point. Alex, have you got that picture that I sent you with the magnetic field on it?
Give me a second. I have to have it somewhere. This one?
Yeah. I suggest it's got nothing to do with Coriolis. It's all to do with that and the fact that the pendulum itself is magnetic, and it governs what governs that movement that you're describing is actually that. And the position, the orientation that you get the swing in. If you swing it north to south, you're going to get less of that effect. But if you swing it east to west, you're going to get it more, because the magnetic field lines of the Earth are going to influence it. I don't think it's got anything to do with the Coriolis effect, and I don't think you could disprove it one way or the other. But what I'm saying is it's the contrasting argument for the Coriolis effect, and I don't think either of us would be able to prove one or the other, because although we know that magnetic field lines do exist, most of us generally question the Coriolis effect at all, because reasons.
Actually, there's a great thing that I can tell you about the Coriolis force, and that is basically the directional dependency of the Coriolis force. The Coriolis force, interestingly, does not affecting anything that is at rest in its position on the Earth. It only affects things that are moving and makes them appear as if they take a curved path.
Okay, so
basically,
if
the Coriolis force is the cross product of, hold on, let me take a look at my screen again, is the cross is 2 times the mass times the axis of rotation of the Earth, cross product with the velocity of the object that it's working on. What that cross product means is, basically, I already told you what those letters with an arrow above them mean. They're basically giving a direction in 3-dimensional space. So, hold on, gotta zoom out again. If you've got basically one vector in this direction and one vector in that direction, then the cross product of those 2 vectors is going to be perpendicular to all of those 3 vectors. So basically the right-hand rule, where, hold on, let me make sure. This is the first vector, this is the second vector, and vector in that cross product, and this, the one going outwards, is the end result of that cross product. Now, what that means is, if our pendulum would be going north, so basically here's the pendulum, here's the resting point, and we're looking at it from the top, and it would be moving north, then the Coriolis force would be pulling it to the right. So it would take, if I may exaggerate, such a course.
Agreed.
Now, on the way back, its direction of movement is going to be the other way around. So, as one of those vectors is the other way around, then the force that it exerts on the pendulum as it is moving back down will also be the other way around, meaning it takes a path curved like this. That's basically how the rotation of the Foucault pendulum comes to be. So at this point,
let me address,
as it has arrived here,
let me address.
And yeah,
this is the issue. What you say is the Coriolis effect. I actually believe is the effect of the electromagnetism or the magnetic effect on the Earth. How would you be able to distinguish one from the other using the explanations that you're about to do? How can you say that it is the Coriolis effect doing this or it is not? How would you know?
Because the magnetic, because any constant force on a pendulum isn't going to get it to rotate. If, let's say, this is the Coriolis effect,
any constant
and this
force,
is the magnetic force. Think about this. We've got our pendulum here, and let's say we have it initially here. It's going to swing upwards, and again, I'm going to exaggerate this in a massive way.
Okay.
And let's say we've got the magnetic force over here, and it's going to turn it that way. So
Same
far,
effect
so
as
good.
what you just did before.
However,
Yeah.
the magnetic force is still pulling it in this direction. So even when it's here, it's still going to be pulled in this direction. So instead of moving back this way through the middle, it is going to curve backwards to the point where it came from. So assuming that the magnetic force is massive and we've got an incredibly high gradient, then the pendulum.
Hector, draw in the return line the way that you were just about to, but stopped.
I did draw in the return line. It's exactly on the path of the forward line.
Why would it be like that and not like the first diagram that you drew?
Because in the first diagram, as our pendulum is moving this way, the Coriolis force is basically rotated 90 degrees to the right from its direction of movement. So as we're moving, as we're moving up, my pen is now the movement direction of our weight at the end of the pendulum, and this is the direction of the Coriolis force. Always a 90-degree turn to the right. We're moving up here, taking a break, and then turning around. The Coriolis force is still 90 degrees to the right, so now it's up there, which means that instead of being pulled this way, so back, it's going back to its original point, it's going to be pulled that way because the force is now, from our point of view, the other way around. So it's going to go up here, as it's going to turn around from here. The force is again 90 degrees to the right of it.
I agree with that part of it, the Coriolis part, but I don't agree with what you've said on the right, which is the representation of the effect of the magnetic influence on it, because the magnetic influence would create the exact same curve on the way back. It wouldn't.
No. The thing is with the magnetic force.
Hang on. Let me explain why. Because on the one where on the right hand side where you've shown the thing and its first pass, For it to follow the same line coming back, it means that the force, the magnetic field force, must be pointing the opposite way, because if it was pointing to the right, then it means that it would follow the exact path on the left that you've drawn on the illustration.
No. Wait, hold on a second. This, without the magnetic force, the pendulum would go that way. So through the middle and somewhere over here.
No, it wouldn't.
The pendulum is here. Its middle point is here. If there were no magnetic force whatsoever, where would the pendulum go? If it were just going to swing below.
It would go in a straight line, arguably, unless there were other forces affecting it.
And if there's a force pulling it to the right, or that's to the right, it would end up further to the right. Correct or not?
But it would represent itself with figure 1.
No. In figure 1, the exact same reason why it's going to take a different path on the way back is because the Coriolis force is in the opposite direction.
No, you've got it wrong. That's not. I agree that point with the Coriolis force, but what you're demonstrating on the right with the magnetic field lines is not right. What you would get exactly the same results.
Then please explain to me how on the way up, the magnetic force is pulling it to the right, and on the way back, it's supposed to pull it to the left.
Because it creates the own torque. When the pendulum is moving, the Coriolis effect doesn't, right, you've exaggerated it on illustration 1. On illustration 2, when the pendulum gets to its extremity, if the magnetic field lines are affecting it, it will go back the exact same way that you've demonstrated in field 1 because of the torque created by the pendulum itself when it swings. It's the same thing. It's not going to do the opposite.
Here the force is always the same. Here it's always the opposite. Why should those two be the same when the forces are different?
The forces are the same. You're saying the forces are different. I don't agree. The forces are the same.
Yeah, Anthony, the difference is that, wait.
I got to tell you where the Coriolis force is coming from.
Wait, Hector, just give me a second. Anthony, in the left picture, the force that is applied to the pendulum is dependent on the movement of the pendulum. It's always in the direction of the movement of the pendulum. It's always going to the right side. But
actually,
wait. But in the with the magnetic force, it's always going to point to the center of the magnetic field, or one of the poles of the magnetic field, to be more exact. And that is, per definition, always the same direction. That's why the forces are completely different.
In figure 1, if the Coriolis force is the thing that's influencing what's happening, the pendulum would swing in a straight line. It wouldn't swing in a curve. The pendulum is supposed to be the pendulum isn't supposed to be affected by the Coriolis force at all. That's why the pendulum is supposed to be the authority for the rotating Earth. The pendulum should swing in a straight line with the Coriolis force because it's the ground that moves, not the pendulum.
It's exactly the opposite way around. Basically, the Coriolis force is an effect that only occurs in a rotating frame of reference. If our frame of reference would not rotate, there would be no Coriolis force. Basically, it's two ways of describing the exact same problem. You can either describe the pendulum and our system of reference as being at rest and the Earth moving below it. In that case, you've got basically the turntable rotating under the pendulum, as we've already explained. If you want to explain the thing, looking at it from a rotating frame of reference, it will look as if, when you look at the pendulum from the rotating frame of reference, as if there is a force working on it.
Yeah.
And this force is the Coriolis force.
So you're citing
basically this force explains how explains to a person looking at it from a rotating frame of reference what the person from a system of reference that is at rest sees as no force.
So you're basically, what you're illustrating is the results of the Sagnac experiment, where if you're on the spinning disc, then it appears as though you're not moving, but if you're off the spinning disc, then you can see that the thing is moving. And the results of that said that you can't tell if you're on it or not. And this is kind of the point that you're illustrating, because
no,
the pendulum is moving if it is the Coriolis force, the pendulum is moving in pretty much in a straight line. Do you not accept that?
Basically, all right, back here. The Coriolis force is the cross product of the rotational axis and the velocity of our object. If our pendulum is at this point right now, it's not moving. So the only thing accelerating is the gravitation that's going to pull it towards the center. As it's going further in, it starts to move, gains a velocity, and as it's now got a velocity, it's going to be pulled to the right due to the Coriolis force.
No,
which means
no, that's wrong. It's not. It's going to resist any forces because it creates its own torque. You're wrong. The minute that velocity gets to a certain point where it's the biggest effect on the pendulum, no other effect is going to influence it because its own torque creates it. So you're wrong.
What do you mean by torque, to be precise? Because I've got no clue what you're talking about here.
Right. When the pendulum is building its velocity and it's about to get, welcome back, and it's about to get, when the pendulum is at full stretch and its relative speed is 0, as it begins to move its speed back up to its full swinging speed, there is a point where, as the velocity increases, the torque that's created by the swinging pendulum itself resists all other forces because the pendulum itself is the resistance. Do you understand that?
You mean you basically need a certain force to actually do anything with a pendulum, or do you mean in a stabilizing way like the gyroscope?
Yes, just like the gyroscope.
Oh, I think I get where the problem is. Do you know how the stabilizing effect on a gyroscope works?
Centrifugal force, yeah.
Nope. Actually, it's inertia.
Yes.
Imagine you've got a gyroscope.
We're talking the same point. How you tell me how, based on your drawing, the inertia of the pendulum is able to be affected by Coriolis, because it's only if it is to be affected by Coriolis at all, it would only be at the extremities of its swing, and it would stop the minute it gets enough velocity to overcome it, which wouldn't take long.
You remember in the video that the guy showed where basically he had the gyroscope rotating around this axis, and he pushed it here. It started to very quickly rotate on its own in this direction.
No, that's not what happened. When he pushed it in that direction, the gimbal moved with it.
I mean, he applied a torque on the pendulum in this way, and the pendulum responded by turning itself in another direction. This is called precession. The basic effect is
right.
That's not enough space to draw it. Hold on. Give me a second.
Right, listen. Even if I don't agree with you, because as the velocity increases from a static position when it's at its full swing, the pendulum will resist all other forces once the velocity gets to its point where it's able to do that, and it will do it pretty much straight away, because
hold on a second.
The alleged Coriolis force is so small, it doesn't need much velocity to create its own inertia.
All right. Let's imagine you've got a gyroscope here. It's rotating this way, so this way around. Now, there's the axis of the gyroscope, and you're trying to turn it this way. So basically, the piece of weight here on the left side is going to be accelerated this way, and the piece of mass on this side is going to be accelerated that way. Now, our gyroscope is rotating, let's say this way around. So that piece, which is moving this way, is going to move down here, and the piece that was moving this way is going to move up here. So now, due to inertia, the gyroscope will want to rotate this way instead of that way that you initially pushed it in. That's how the stabilization of the gyroscope works, in effect by rotating the torque you apply to it. Does that make sense?
It does, but that's not how it's working. Listen, right, with regard to the physics, can we move on from the physics? Because it's going to be subject to the results that we obtain.
Everything we wanted to talk about here is physics.
I thought we were actually going to be talking about how we're going to conduct the experiment and what we're going to
actually. Yeah, that's why I asked in the beginning if you all understood the physics, so we could talk about the results that you would expect.
Well, I'm not a physicist, and I don't really need to understand how the physics works. But what I'm asking is, are we not better spending our time talking about the experiment and how we're going to conduct it to achieve the result?
What I was telling you was explaining why magnetism isn't even remotely going to affect our experiment.
No, I don't agree with you. I think that you misunderstand the effect of the torque created by the pendulum itself once it gains to enough speed to overcome it. Well, the reason why
Anthony,
it does is
with all due respect, but I think you've got no clue what you're talking about here.
turn over the page, start a new page, and I'll explain to you the reason why. So just draw the pendulum at rest.
Top-down view or from the side?
Sorry, from the side. From the side. Okay, that's at rest. Now draw it at the extreme to the right. So wherever the point would be where it comes to, so that's the maximum travel of it, okay? Do you agree with me at that point where it's at its maximum travel, its velocity is 0 because it has to go back the other way at some point?
Yep.
When its velocity is at 0, what's the biggest force that's affecting that pendulum itself?
Gravity.
Well, it's neutralized by at the point where it's no longer moving, literally the point where it no longer moves. Is it in a state of equilibrium or not?
Nope.
Why not?
Because it's going to be accelerated out of that away from the turnaround point.
I agree. It is going.
Equilibrium is going to remain either at rest or at the same velocity that it is right now. And
hang on.
The pendulum here is going to be accelerated in, so it's not at equilibrium.
Wait. It's going to be. It isn't yet. It's at the point of rest. It's at the extreme part of its swing. It's got no velocity. It's just come to a stop and it's just about to go back the other way. Before it starts moving again and it's at 0 velocity, you're effectively in the same position as you are at rest.
No.
You are.
Hold on. Let's just quick go over all the forces that are applied on the pendulum here. So basically, we've got gravity. Gravity is always there. So
can we talk?
This is gravity. And at the same point, you've got the string keeping it from falling down. So we've got a force in, let's say, that direction.
Yeah, agreed.
Correct?
Yeah.
Now, we've got one thing pulling it vertically down and one thing pulling it both up and a little bit to the side.
Yeah.
So if we add both of these forces together,
at the point when it's
arrive at a total force that is going to pull our pendulum this way.
Yeah,
that's the thing that's going to accelerate it back in.
Before we get to that point where that arrow comes into play, that third arrow you just drawn, when the pendulum comes to rest in that position, what forces are affecting the pendulum?
Gravity and the string.
So we agree there's no velocity, and the effect of the gravity is going to send it back the other way. So the pendulum is effectively in a state of equilibrium because the only force that's stopping it from moving any way is the velocity that's no longer there, but it's about to get it. Agreed?
In order for the pendulum to be at equilibrium, basically, for all the forces acting on it to be 0, there would need to be another force holding it back, basically pulling it this way.
Yeah, that's the lack of inertia, isn't it? The lack of velocity.
No, not really. The forces in this case, none of the forces is dependent on velocity.
Well, it is, because the next force that applies to the pendulum is dependent on the velocity. The velocity must equal 0 before the negative side of it, pulling it back the other way, can occur. So it has to reach 0. Agreed?
I'm currently trying to translate what you just said into things that I understand.
Right, the pendulum's velocity, whatever the pendulum's velocity is, when it gets to the extremity of its stroke, the movement of the full swing, when it gets to the extremity, the velocity equals 0 before it starts going back the other way. Agreed?
Yes.
So at that point, the only forces that are affecting that pendulum, because it's metal, are the magnetic fields of the Earth.
No, there's also gravity and the force of the string.
No, because gravity is being countered by the string. So gravity has 0 effect on it at the point when it's...
Not completely. The string is pulling it slightly sideways. Gravity is pulling it down. So in total, if you add these two forces, you get a force pulling it this way.
Agreed.
That's the whole thing that makes it move.
Yeah, but
that force is always there. The only place where those forces perfectly cancel each other out is here at the equilibrium point.
Wait, where? There?
Yeah.
No.
Because at this point, the string is pulling it exactly vertically up, and gravity is going to pull it vertically down.
Wrong. That's wrong, because if what you just said is true, then there is no gravity or string affecting it, and that's not true, because the gravity in the string is still...
The gravity is still there, but it's completely counteracted by the string. This is not the case at the end of the movement, where...
You're wrong. You're wrong. At the end of the movement, it's the same effect. It's the exact same effect. The only difference is, because the string's on an angle, the gravity pulls it back the other way.
In the middle, you don't have any net acceleration at all. On the outside of the swing, you have.
Agreed. But you need that angle for it to start its velocity again. So when you say when it's at rest in the middle, you're saying that there are no other forces affecting it. Gravity's still affecting it, and the rope's still affecting it because it's countering the gravity perfectly. So it's in a state of equilibrium. It's exactly the same when it's at the full stroke.
Equilibrium means if you add all forces together that work on it, you get zero. Basically, all forces cancel each other out. That's not the case. Exactly.
It is the case. Why is it not the case?
Hector, do me a favor. Between the resting point and the outside, can you draw the pendulum again? The string and the mass?
Between the resting point?
Like at position 0.5, maybe.
All right. Yeah, so
because I think I understand what your problem is with it, Anthony.
No,
Anthony, could you draw in, or could you tell Hector to draw in where there are net forces now, or where there are forces now acting on the string?
Where the forces are acting on the string or the pendulum?
Or the pendulum, sorry. Where are the forces that are at that position acting on the pendulum? In which direction do they go?
It's the same three arrows that you've got to the pendulum on the right.
Great.
So basically, I've got one arrow towards the top here on the string.
Yep.
And I've got one arrow down here, basically down towards the center of the Earth.
Which is the
correct?
Gravity. Correct. And you also have the inertia. You also have the velocity.
Which one would the velocity be looking at, do you think, Anthony? To the right or to the left?
To the left.
That's not your velocity. That's the acceleration.
No, it's velocity. At that point, it's no longer acceleration. It's already got to its speed.
Wait. Are we coming from 0 to 0.5, or are we coming from the left, or are we coming from the right? What are you describing?
Well, we're coming from the right, where it's just been. It's now
from the right. Okay.
Hold on, Anthony. 1 second. Quick chapter on adding and subtracting forces.
No.
Just so we can get the basics done.
I think I understand what he's misunderstanding.
Okay.
Can you please go back to the drawing?
Yeah.
And Anthony, same case, but this time the pendulum is coming in from the left, so it's coming from 0 to 1.
Yeah.
Do you agree that the forces are still the same? One is pointing left, the one is pointing down, which is gravity, and the third one is the stabilizing force from the rope.
Which was the first one?
Pointing left.
It would be pointing right.
No, it isn't. That's the thing you don't understand. At that position, the third force is always pointing left.
No, you said it was swinging back from the other side.
Yes, the force itself is still pointing left.
No, it isn't.
Right, Hector?
The force, it's Anthony, you're confusing force and inertia
with momentum. That's what I'm suspecting.
Force and momentum.
Yeah.
Basically, momentum is a measure for how hard it.
Whoa, hang on. So what you're saying is when the pendulum's swinging from the left and it's going out to the right, you're saying the force that's applied onto it is pointing left?
Yes, that's why it's becoming slower.
Basically, if you've got an object, let's say an object with a certain mass,
in that case,
it's moving, this is the velocity.
Hector, go back to the picture.
The force applied to it. What's happening to it? Just
Hector, go back to the picture.
1 second. Just so we get this through. Basically, what's happening?
I can show you this. Go back to the picture. So if at this point, just draw in a -1, a -0.5, and a -1, just so that I can I'm clear with what's supposed to be happening. Just on the horizontal axis, just do a -0.5. Yeah, that's it. Alex, are you saying that the pendulum's coming from -1 and it's gone through -0.5, it's gone through 0, and it's now at +0.5? Is that what you're saying?
Yes. It just Hector, draw at 0.5. Just draw the direction in which the pendulum is going. That's easier, I think.
Yeah.
Just draw that it's going to the right.
I need a little bit more place to draw. This is going to get a little bit cramped, and I'm going to use separate colors.
Actually, no. I'm going to do it. I'm going to do it in Paint. Okay. I think that's better.
No, this one.
This
way it's
just
easier.
about to deal it, to address it.
Okay, so Anthony, the point is that the net force that is applied to the mass or that acts on the mass always points towards the center of the pendulum. And that's something I don't think you understand.
But it's an irrelevant point because it still doesn't change what
No,
we're
it
talking
isn't.
about.
It isn't. It's the complete. It's the thing that you don't understand.
No. It's an irrelevant point because at the point where it's at 0.5 plus 0.5, and it's come from minus 0.5.
All right.
The forces that are on the pendulum are the two that we've just that we're not in disagreement over. But the slowing down force at this point is very, very small because it hasn't gone far enough through its stroke to gain the force required to stop it.
So just for simplicity's sake, can we just say we are using this direction as the direction of our movement?
Okay.
Yes.
So let's say this is position 0, position 1, position 2, position -1, position -2. Just for more scale. Now, I'm going to draw in all the forces that are going to work on our pendulum. So first gravity.
Agreed.
Here. Gravity.
Yes.
Here.
Yes.
Gravity here. Gravity here. Gravity here. And we've got the force due to the string holding the pendulum back. So it's the force here.
And what we're going to describe this force as?
That's the force due to the string.
Yeah, we'll call this the deceleration of gravity. Or the limitation of gravity.
Let's just call it the string force.
Okay.
This is the gravity. All right, I'm just gonna save the time. Now, we're talking about movement from here to here, right?
Yeah.
Yes.
All right, so at this point, we are at rest. At this point, we're going this way. At this point, we're going this way a little bit faster. At this point, we're going this way a little bit slower. And at this point, we are at rest again.
Right.
No, see, I don't agree with that. All the points of velocity are all going to be horizontal points. They're not going to be angled.
So if we're only moving horizontally, how do you get from here to here?
Horizontal. It's a horizontal force.
There's a vertical component in there that Hector's right about it.
Hold on, I'm going to be AFK for a second. My mom just came home. I'll be back in 5 minutes.
5 minutes. Okay.
Okay.
So Hector's right about the vertical component, because if you had just horizontal movement, you wouldn't lift up the pendulum.
No, because gravity would be pulling it down.
No, the movement is just the velocity. The arrow that Hector is drawing is just the direction in which the pendulum is going.
Okay, in that case, I agree.
Okay, yeah, then that's all.
Alex, did you really think that Reds was coming in to discuss this, or did you know in advance that he was coming to bash?
He told me that he was going to not to do it about 5 minutes before you entered.
So so basically he dishonestly agreed to come into the hangout so he could get my attention, and that's all he was doing.
No, he didn't say anything about what he would do in the hangout at all. I think he might consider doing the experiment and first of all listen to what you had to say.
All right, I'm back.
Okay.
He isn't going to do it.
All right.
He isn't a credible witness. He's an asshole. But anyway, go on, Hector. Carry on.
All right. Now, do you know how you get the total force working on an object by looking at all the forces that are working on it?
Well, there's only the one force that in physics would be applying to the pendulum at this point. Agreed?
There's actually a lot of forces, but most of them are far too small compared to the other forces working on it to do anything.
Right, and I'm only interested in the movements, the forces that are affecting it whilst it's in a state of zero, which is at the end of the stroke. But We're not going to get
You
to
mean
there
by
just yet.
2, you mean in the position 2 and -2?
Yeah.
Okay.
Well, are you not going to make a point about Coriolis or something? Where were you going with this?
For now, I think you wanted to talk about the force due to magnetism and not Coriolis force.
Oh, okay. Well, I thought you were
Because
going
the Coriolis force in this case would be either pointing exactly downwards or upwards, and the problem is I can't really point
No. That's
down and up, and that because if I did that, it would get a little bit too confusing on that space I've got.
No. Let's address the Coriolis force. You said the Coriolis force points down. Is that what you said?
It's pointing away from the camera. That's the point. He can't draw it on the paper.
Hold on, 90 degrees to the right. So in that case, it would be pointing down.
No, it wouldn't be pointing down. That's gravity, man.
Yeah, gravity is pointing downwards in this direction, and the Coriolis force would be pointing into the paper. So this way.
The Coriolis force will be pointing into the paper. Do you mean? I'm not sure I understand what you mean when you explain Coriolis.
The system he's drawn now is two-dimensional. We would need a third dimension to describe the Coriolis force in this drawing.
So do we agree at this point that the Coriolis force manifested on that drawing would be towards the camera and away from the camera?
Yes.
In this image, for the direction to the right, it would be away from the camera.
Yes, I agree. So
no, towards it. If it was moving from left to right, then it would be moving towards it, wouldn't it?
Well, hold on.
Well, it wouldn't matter. It'd be one way or the other, but the point is it would be going towards the camera or away from the camera. Agreed?
Yes.
Yeah, okay. And drawing that on a flat paper is kind of hard to make it in a way that's first clear and second not too confusing with all the things we already got there. So
just for the sake of physics, Hector, can you please draw in the other forces?
Yes, that's what I was going to say. Draw in the other forces that you believe are affecting it.
No, not the Coriolis force, just the acceleration from gravity.
You mean the total force?
Yeah.
All right. The total force would be, I'm going to use a different green here to make it clear that this is not a initial force, but the sum of everything.
Maybe do it in pencil so you could tidy it up afterwards, because we've got a good template at the moment.
It's nothing that I couldn't repaint. Here it's 0.
Yeah.
So let's just put some rough values in on there, just because obviously the values at -2 and +2 are different to the values at -1 and +1. Agreed?
The direction is different for 2 and -2 and 1 and -1, but the total strength is the same.
All right, no, yeah, but the force of deceleration, if it's coming from the left to the right, the force of deceleration at point 1 is minimal, but the force of acceleration, it's accelerate. Yeah, so it's a minimal force at 1, but it's a maximum force at 2, because it has to be enough to stop the pendulum. Agreed?
Yeah. It's smaller at 1 than at 2, but it's not a whole ton smaller, probably half of it.
Yeah, that's what I mean, half. So we could say that the force required at 0, at +1, we could give that a value of, say, I don't know, it doesn't matter what the units are, so we could say 5, and then the force required at 2 would be 10. Agree?
Hold on. Graphs. So, force. Direction.
Yeah, it'd be an exponential.
I think Alex has been thrown out again. And strength of the force.
No, it's not a straight line.
That's what I was talking about earlier with linear systems and nonlinear systems.
Welcome back, Alex. So if you draw, why did you draw a straight line then?
Because for now, I'm assuming that we're still in the linear regime, because if we're going into the nonlinear regime, we again have a lot of points that we have to take into account on. And if we assume that we are still in the linear regime, it's going to be easier to address the point of magnetism.
Well, No, practically, if we're going to apply physics, it needs to represent the reality that you claim that we are representing. So you have to do it with a sine wave because, or I don't know whether that's
All right,
the correct.
then let's turn this into a sine wave.
Well, I'm not saying that that's the correct one to do, but it would be an exponential curve, wouldn't it? It would
All
start.
right, now it's a sine wave.
Well, it wouldn't represent itself like that, though, would it? It would start off very small at the beginning, rise into a big absolute at the end, and then it. Alex?
Yeah.
Are we still here? All right, it's got.
Yeah, yeah, it threw me out again for some reason. I don't think why it keeps doing that.
It's okay, Hector. Basically, Hector, what you need to show is not a linear line, but in any event, my query would be, let's talk about the point where it's at 0 rest at 0.8. Sorry, at 0.2.
Yeah.
Because that's the point. That's the point where Foucault's pendulum seems to fail, in my opinion, and it's the reason why we're going to get dodgy results. Because when it's at rest at 0.2, it's neither traveling one way nor the other. It's at a point of rest. Agreed?
Yeah, at this point it has stopped.
Right. So at the point it's stopped, what other forces, if any, are being applied on the pendulum?
We are at 0.2. Our force strength is here.
Yeah, at 0.2. What other forces, if any? Because you suggested Coriolis. I think that affects nothing to do with the pendulum, but you suggested Coriolis. Do you still maintain Coriolis?
Force would be. Hold on. The speed is a cosine curve. So for left to right, the Coriolis force would be something like this. And now, from right to left, it would be exactly the other way around, since the pendulum is moving the other way.
And now, are you not actually drawing there, rather than labeling it the Coriolis effect? Are you not actually drawing the value given to? Let me see. Because that's consistent. The lines you've just drawn there are both consistent with the rate of acceleration, or rather the rate of velocity of the pendulum. Agreed? As the pendulum goes to its maximum, the velocity goes up and then stops.
Yeah.
And then it comes back again. Are you not actually drawing a velocity curve and describing it as Coriolis?
Well, both the curve for the Coriolis force and the velocity curve are going to look the same, because the Coriolis force is directly dependent on the velocity curve.
Great, okay.
It's basically velocity times a constant.
Okay, so at this point then, so what you're saying is the Coriolis effect has no effect when it's at values -2 or at +2. Is that what you're saying? Okay, so the Coriolis is right. So this is good for me, because I'm saying that there's a force in play when it's at 0.2 and at -2 that you've just ruled out. Okay.
Which force would that be?
The magnetic field forces of the Earth. Because
yeah, but that it would be identical on every point of the curve.
No, it wouldn't. It wouldn't, because it wouldn't.
Hold on, Anthony. Why is the magnetic force of a different strength at different points in this curve?
Relative to the velocity of the pendulum and the inertia that's created by the velocity of the pendulum, the force is the same, but at the point when it's at 0, it's the biggest force on the pendulum, because there's no other forces in play.
Gravity is still in play, and the force due to the string is still in play.
No, gravity is not in play. The pendulum's it's at rest at 0. It's not moving.
Why should there be no force of gravity acting upon the pendulum when it's at the point 2 or -2?
Because if gravity was affecting it, it would be moving. We're talking about the point when it's come to a standstill and it's stopped.
Oh, Anthony, I think I might have found the issue here. An object's speed and the force that is accelerating it are only the dependence is only in one direction. Basically, if you want to accelerate a car from stopping, you have to put you basically have to put press on the gas, and you have to put force on the wheels to get your car moving.
Agreed.
If there would be no gravitational force at this point, then our pendulum would be at a standstill, and it wouldn't be moving back towards the middle.
That's exactly what happens.
So you're saying that as the pendulum swings up here and it arrives there, it just stays there and never swings back towards the middle?
No, I'm saying there comes a point where its velocity is 0, and then it starts to swing back the other way. Do you not agree with that?
Yes, at exactly one point in time, the velocity is 0.
Agreed. So now we've established that it is at 0. The only forces that are affecting that pendulum, gravity's not affecting the pendulum at this point because its velocity is 0.
Again, gravity is not depending on the velocity of an object.
But it is in this instance, because if the gravity was anything, if gravity was affecting the pendulum would be moving.
It would be accelerating. That's the difference.
We're at a state of
Forces
0.
create acceleration.
Whoa. Wait. We're at a state of 0. So at this point, is gravity? It's a black and white yes or no.
0
is gravity affecting the pendulum or not?
Yes, gravity is affecting the pendulum. It's always affecting the pendulum.
But it's not doing anything because it's not making it move.
Yes, it is making it move. If gravity would not make the pendulum move, it wouldn't move back towards the middle.
No, it will move back towards the middle because gravity becomes the more stronger force. But at the point when it's at 0, gravity is being equaled by the strength, the torsion of the rope, and the loss of inertia. Gravity only becomes the dominant force as the acceleration increases. It needs the gravity to pull the pendulum down to create the velocity. But at the point where it gets to 0, the gravity is being equalized by the lack of velocity itself.
Okay. Let me think about for a moment how I explain that to you in the best way.
You don't need to. The pendulum is at 0. There is no velocity. It's in a state of equilibrium. You don't agree, but it is.
Again, you are confusing force and velocity here.
No, I'm not. What you're doing is explaining why gravity is affecting the pendulum, yet we know that the pendulum is at rest. Its velocity is 0. So at that point, gravity is doing nothing.
If you take a tennis ball and throw it in the air, there's going to be a point where its velocity is 0, but it's still got a certain weight to it, which is why it's going to be accelerated downwards by gravity again.
At the point when it's at 0, gravity is doing nothing.
Yes, it is. It's accelerating it downwards.
No, it's not, because it's at 0. If it was accelerating it downwards, there would be a speed.
No, there's an acceleration.
Yeah.
There's a difference between acceleration and speed, Anthony.
I agree. But the fact that it's at 0 means
acceleration can be unequal 0 if speed is 0.
Right. If the pendulum
acceleration is the rate at which the speed changes. Basically, hold on. If let's say we have an object where this is the object's velocity and this is time, and we've got just some kind of curve, then acceleration would be basically, if we want to know the acceleration at point 1 or point 2, then what we'd need to do is measure the slope of the curve. And in essence, acceleration is the slope of velocity. So in essence, if I now draw the acceleration of that object down here, we'd have, okay, here the slope is 0, here it is 0 again. This part it's going downwards, and this part we have a rather constant acceleration. So basically, this is your acceleration. This is, we're at 0 here.
There's an easy way to demonstrate this.
Basically, what I'm saying is, this is basically the slope of this. Acceleration, in essence, is the slope of the velocity. And basically, if I draw this below 0, the acceleration here is still unequal 0, although at this point my velocity is 0 because I'm going from moving backwards, stopping, and then moving forwards. My velocity can be 0 at one specific point in time when my acceleration is larger than 0 or smaller than 0.
No, it can't.
Acceleration is the rate at which my speed changes.
Yes. But
velocity is the speed itself.
Hector,
Think of it as someone having a negative bank balance and earning a certain amount of money per month, and at some point, and basically his income is the rate at which his balance changes. At some point he's below zero, then he's at zero, and then he's higher at zero. With your monthly income, you get it in steps, which isn't really that representative of actual physics, because in physics you get everything constantly, where basically with your bank balance you'd probably be at zero or a fixed value for a certain period of time. Your velocity is only going to be zero at one exact point in time, one specific point in time. Basically, the amount of time that your velocity is equal to zero has a length of zero. Because you're only at a velocity of zero for one specific point in time, after which your velocity is different to zero. Because your velocity changes with time as your acceleration isn't zero. If your acceleration were zero at one point, then basically the curve of your velocity would be flat. So you'd be at zero for an extended period of time.
Exactly.
And you are not at zero for an extended period of time when your pendulum's there. You're only at zero for one point in time, a point.
Exactly. That's the point I'm talking about. So in the top right-hand corner of the page, just draw a straight line at the bottom of that gap. So that we'll call that the earth, the ground. So just draw in that top right-hand corner. Yeah, that's perfect. That's the earth. Imagine you fire a tennis ball up into the sky with a gun, for example, so that you get a velocity.
Yeah.
When it gets to the highest height that it can get to, but before the point where it starts to fall back to Earth, do you agree that its velocity is zero?
Yes, at that one point in time, its velocity is zero.
Great. Now, draw the tennis ball at the highest point it can get to. Is it in a state of equilibrium at that point?
Nope.
Yes, it is. All forces on the tennis ball are zero.
If all forces on the tennis ball would be zero, it would not be accelerating.
Exactly. We're at the point where it's at zero.
If the tennis ball has a velocity of zero and an acceleration of zero, it would be staying up there and not fall back down to Earth.
Agreed. But gravity at this point is not affecting the tennis ball, and we know that because it's not falling back to Earth.
So you're saying, hold on, the tennis ball is not falling back to Earth. I'm going to test that right now with my pen, throw it up, and see if at its highest point on its trajectory, it's going to stay up or fall back down.
No, I'm not saying it's not going to fall back down.
It fell back down. You're wrong, Anthony.
What you've just done is what Neil deGrasse Tyson did with his microphone when he illustrated gravity, and that's not what I'm asking you to do. What I'm asking you to do is draw on the tennis ball what forces are affecting that tennis ball when it's at that point, at the highest point.
Hold on.
Bear in mind its velocity is zero. No. There is no force there because its velocity is zero.
All right. Then tell me what makes the gravity stop affecting the tennis ball there.
Buoyancy. It gets to a point where its velocity has got to zero and it's in a state.
Buoyancy?
Yeah, it's got to a state of equilibrium.
So in essence, you're telling me that the tennis ball at that point magically becomes light enough to float in the air?
Effectively, yeah. That's exactly what happens.
Dude, do me a favor. Grab a scale, grab a tennis ball, and measure its weight.
5 grams.
How big's the tennis ball?
I don't know. Does it matter? You could do it with a human.
The point that Hector is trying to say is that you will be able to measure the gravitation even if the object is at rest.
But you couldn't because it's not moving. If the force of gravity is affecting the tennis ball, it has to be moving. When it's in a state of...
You know how your scale works?
You wouldn't be able to use scales at all.
Scales work by measuring how strong an object pushes down on the pressure plate on top of them, and then determines, okay, it's pushing that strong down on me, so it's that heavy. That's how scales work.
You're not understanding what forces are in play. When it's fired out the cannon or the gun, the force is not gravity that's affecting it. It's the acceleration of the explosion. Agreed?
Yeah, at the point where we're firing it, we're pretty much kicking its ass quite hard if we're firing it from a gun.
So as it gains in altitude, the force that's still in play is still the velocity. The force that's affecting the velocity is the inertia, or the, what's the word I'm looking for? No, it's not the inertia. It's the velocity.
Inertia is not a force.
It's the velocity of the tennis ball is, what's the word I'm looking for? Right, at the point when the tennis ball gets to its highest point, gravity is not affecting it because it's not moving. Gravity's effect is it forces an acceleration. Agreed?
Yes, gravity is an accelerating force.
Yes. So at the point when it's not accelerating, which is the highest point it can be, gravity cannot be affecting it because it's in a state of equilibrium. Its velocity has been matched and equaled by the force of gravity, but it's had no effect until it starts to move because it's a force of acceleration. Agreed?
No.
Yes, it is.
Anthony, where did you get that from? Just out
Because
of sheer curiosity, where did you get that from?
The tennis ball is not moving. There are no forces in play on the tennis ball. When it's
There's a difference between not moving and no forces being at play. Yes, it isn't moving. Yeah, but no, there are forces in play.
What? What forces are in play?
Gravity.
No, it's been countered by the velocity. The velocity's got to zero. Gravity
is not a force. You cannot counter a force with something that is not a force.
But the velocity is what counters the gravity.
How does velocity count? How does a movement counter a force?
Because you fired it out the gun. That's created a velocity which is needed to negate the effects of gravity until it loses its velocity. It gets to a point where it's being. I don't know why you don't understand this. When it gets to its highest peak, there is no forces applied on it at all. It's only as it starts moving again by gravity, then you start seeing the effect of gravity. But at that point at the top, nothing's in play. It's in a state of perfect balance. Which is the issue with the pendulum. When the pendulum gets to its complete extremity of its stroke, its velocity is zero. So at that point, it's balanced perfectly against gravity and the velocity, creating zero. So basically, velocity equals zero and gravity equals zero. Otherwise, it would be moving.
Again, that's the difference between velocity and acceleration. Those two are not the same. They are connected.
They're opposite.
But they are not the same.
They're opposite in this instance.
No.
Yes.
Your velocity can be zero even if your acceleration is not zero. However, in that case, your velocity can only be zero at one point in time.
No, it can't.
If at one point...
You've contradicted yourself with empirical evidence. Your velocity and your acceleration cannot... You can't have one without the other. Once you hit zero, if your velocity is zero, then you have zero acceleration.
All right, you're saying if an object is at zero velocity, then your acceleration must also be zero.
Correct.
And you remembered how we talked about acceleration is the rate at which the velocity changes. Correct?
Yes, but it isn't.
And you agree with me on that acceleration is the rate at which velocity changes, right?
Acceleration is the rate at which the velocity. Yes.
Okay. Your velocity is zero, and your acceleration is zero, which means that your velocity will stay zero, as the rate at which it changes is zero as well.
Yes, that's exactly what happens.
So your velocity is zero, and it remains zero.
No, because the next force that happens is
if
gravity.
Your velocity changes.
Yeah.
Then that means you have a change of velocity. And a changing velocity means that you have got an acceleration that is larger than zero.
Yes, but that's not at the point of where the tennis ball is at its highest point. At its highest point, the only forces that are affecting that tennis ball are the future forces, because whilst it's in the state of zero up there, nothing is affecting it. Gravity pulls it back down, but nothing is affecting it, because otherwise it would carry on going up.
What?
Gravity is a slowing down force against a tennis ball. Agreed?
It's slowing down against a tennis ball moving up and accelerating for a tennis ball that's moving down.
Agreed. So when the tennis ball gains its maximum altitude, gravity becomes the stronger force and pulls it back down. But at the point when it's reached its highest altitude, the tennis ball is being matched by the velocity loss rate and the velocity and the gravity that's going to pull it back down the other way. It's in a perfect state of balance at that one point. So the only
Out
force...
of curiosity, essentially what we're doing here is a physics exercise from 8th grade. Did you have physics lessons at school?
No, we're effectively not doing a physics exercise from the 8th grade. What I'm trying to say to you is there is a balance in equilibrium on the tennis ball at its highest point, and you don't agree. If there wasn't a balancing point, it wouldn't be stationary.
Dude, with all due respect, but I don't think you know what you know what an equilibrium means or how gravity works.
I understand how gravity works, and I know what equilibrium is. Right. So what you're saying is that there's no equilibrium at the point when the tennis ball gains its highest point. Is that what you're saying?
Exactly, because
well,
equilibrium means that all forces acting on the tennis ball would even each other out.
Yeah, but they're all zero.
No, gravity's still there. That's the mean thing about gravity. It's always there. That's the thing that makes airline companies is so angry, because they have to pay for fuel to get their make their planes stay up in the sky.
Listen, gravity is there, but is it affecting the ball when it's at zero? No, because otherwise it would be moving.
Gravity isn't a force that is creating movement. It is a force that creates acceleration. Acceleration can create movement. However, the connection between acceleration and velocity is not a linear term. It's a first degree derivative.
Fine. I don't have any problem with what you've just said. The issue I have is that you believe that there's a force of gravity affecting the ball when it's not moving in that suspended state. That's not true. Gravity is affecting it.
The ball is not in a suspended state.
It's suspended.
You're not hanging it from something. You've got it just flying vertically up.
No, suspended by loss of velocity, not by anything physical. It's had velocity, it's lost velocity until it starts gaining its velocity caused by gravity. It's in a state where nothing is affecting it.
Gravity is always affecting everything. If gravity were to stop affecting the tennis ball, it wouldn't fall back down. It would stay up there.
Exactly. But whilst its velocity is zero, gravity.
So you're telling me that gravity stops affecting the tennis ball up there, and that it's staying up there?
No, I'm saying that at the point where the tennis ball's at its highest, gravity's effect on it is zero because it isn't moving. Gravity's force as it pulls it down. So it isn't having
What do you mean by effect? Because I'm really trying to understand you here, but
no, what you're failing to understand is what actually is going on with the tennis ball when it's at the highest height. There is nothing affecting it because it's in a state of equilibrium. Now you don't agree, and that's fine. Let's move on because we don't need to agree or disagree on it. If you think that gravity is still affecting the pendulum, fine. It can't ever come to a state where a zero is achieved. But we know that that's what happens with a pendulum. So you must therefore be wrong.
What?
If gravity, right, we're going around in circles. You're obviously not understanding me. As the velocity drops, because it gets to the point where gravity becomes the stronger force, because it gets to a zero speed, the velocity equals zero. The effect on it at that point is that gravity is also zero because it's going to now affect it because it's lost its velocity. Gravity pulls it back the other way. But at the point when it's at zero velocity, there is nothing affecting the pendulum, because if it was, it would be moving. Hold
on. Let's just say we're drawing down the velocity of our tennis ball. So this is the velocity.
Yeah.
And let's say this is the time. Let's say this is the point minus t0 where we fire the tennis ball from our cannon.
Yeah, you're going to
get. This is the point where it arrives where it arrives back at the ground. So
you're going to
starting with a positive velocity, and we end up with the ball going down. So to denote it going down, we'll use a negative value. So
you're going to start. No, that's not what's going to happen.
No straight line.
No, it'll be a curve.
All right. How will it be curved? Like this?
No, the other way.
Like this. No, so like this.
So the velocity would be starting from, what's your value on the left? Is it 0.6?
T0 for
T0.
initial time.
Oh, time. So are we talking about when it starts from moving from the left to the right? When
Basically, this is the point in time where we fired the cannon, and this is the point in time where it arrives back on the ground.
Okay, so its velocity would be small at the beginning, and it would rise quickly at the start. Then it would slow right down, and then it would start to fall slowly. And
this is our firing of the ball.
Yeah.
And this is basically the ball going from falling down to 0 again. What's happening in between those 2 points?
Connect it with a sine wave. But pass through the middle.
All right.
Yeah.
Like this?
Yeah. Effectively, it's got smoother edges to it, but effectively that's what happens. That's right.
So, all right. Now let's go to acceleration. Okay.
Okay.
Another graph. You remember how we talked about acceleration being the slope of velocity?
Okay. The acceleration is pretty much going to be the same graph.
No, not really.
It's not. It's going to start off. The acceleration is going to start off positive.
A small slope. So we're somewhere down here. And we're going to have a
start off fast. It'll crest and then it'll come back down.
So we have a massive spike in acceleration.
Yeah. Then the rate of acceleration will slow.
Hold on.
And flatten out.
This is our slope at the beginning, right? So it's rather flat. So we're, let's say, about here. Towards the middle, our slope is going to go faster.
Yeah.
Until we are there, where it's really fast. So it's going down very fast. So we are somewhere down here, I'd say. And at this point, the acceleration is getting slower again until we are at this point, where it's about as steep as here. So we are again somewhere here. So we've got kind of a cosine curve. And at this point, we again have a massive spike in acceleration as our ball hits the floor and then stay still. Here, your velocity is 0 and your acceleration is not.
Your acceleration has to be 0 at the point where it balances. So your second diagram must be wrong.
No. Remember when we said that acceleration is basically the slope of the velocity? If the acceleration would be 0, that means we would have a flat slope. That means our velocity would have to be 0 here as well.
Yeah, but this is what you're not understanding. At the point where the tennis ball no longer moves, its acceleration point is 0, so it has to pass through the middle. It's not in a state of acceleration.
Where you were wrong.
0. What?
I just showed you where you were wrong in claiming that.
No, but it's based on your drawings that are wrong. At the point where the tennis ball gets to its highest, it has neither an acceleration nor a deceleration. Its point is 0. Otherwise, it would be moving.
Again, that's the difference between acceleration and velocity.
So you think that there's a force in play that's affecting the tennis ball when it's at the crest? No, you're wrong.
Yes,
that's just wrong.
And that force is gravity.
I said, what force is affecting the tennis ball?
Gravity.
It isn't, because if it was, the tennis ball would be moving.
Not moving, accelerating.
Right, but it wouldn't be stationary.
Hold on. Your acceleration equals the force applied to an object divided by the mass of its object, taking into account the direction. Your velocity of an object is the time derivative. Hold on. The other way around. The acceleration is the time derivative of your velocity. Or the other way around, your velocity is the integral of your acceleration. That's the connection. This isn't a constant. Basically, all this is saying, we're not taking the value of this, but we're taking the slope of this. And all this is saying is basically we're doing it the other way around.
At the point when the tennis ball and the pendulum are at their extremity, there are no forces affecting either. There may be forces that are there, but none of them are affecting it at that point. Otherwise, it would be moving. You can't dispute that. You might not be able to explain it, but you can't dispute it because it's come to a state of equilibrium. It's zero. Everything is zero.
In one point, I agree with you.
Thank you.
It seems to be impossible for me to explain it to you.
Yes. And it doesn't matter whether it's because you lack the physics or because you think I don't understand. The point is, at some point, that pendulum and the tennis ball get to zero. There are no forces affecting it. It's in a state of equilibrium. You don't agree with me, that's fine. I don't care whether you agree with me or you don't. But I'm telling you now, when it comes to its extremity, it gets to a point of balance because nothing is affecting it because it's not moving. It may be there, but it's not affecting it because the speed is countered perfectly by gravity. Now, if you don't accept that, then there's a fundamental failing in your understanding of physics because we observe that. Physics hasn't explained it so far. All you've said is...
I just explained to you how something can be under constant acceleration and at one point during that acceleration in one direction arrive at a speed of 0.
No, you didn't. You explained to me that I was wrong.
I did, and you didn't understand it.
No, I understood what you're saying, but I said your bottom diagram was wrong. That second diagram, the bottom one, is wrong because at the point when it gets to its highest, it's not accelerating, and you've shown it at full acceleration, and that's wrong.
All right. You agree to meet with me that the acceleration is the slope of the velocity, right?
Show me that on the diagram.
Big slope.
Are you on the top
big
diagram?
Acceleration. Small slope. Small acceleration.
Yeah, but where's the point where the tennis ball reaches its highest altitude?
There.
Agreed. Where's the point on the bottom one?
There.
Where? I don't see anything.
There.
Right. At that point, there is 0 acceleration. It's neither accelerating up nor is it accelerating down.
If that were the case, then this curve had to be flat at this point.
No, it is flat at that point. It's passing through the 0 point. Right. The top one is correct. The bottom one is wrong. What the bottom one should be is a sine wave like the top one. Passing through the middle.
All right. Then let's see what happens if we had an acceleration that would be a sine wave passing through the middle at 0.
You would get a representation of what the tennis ball's doing.
This is going to be a rather interesting case.
So we're talking about the rate of acceleration only, right?
That's the acceleration. That's our time. That's our initial point.
So what you need on this one right, I'm back. So what you need on this one is we'll show it. So what we'll do is we'll compartmentalize the top left-hand part of the axis to be the point where the tennis ball's on its way up.
Yes.
So the rate of acceleration is highest at the beginning, and it flattens out to 0 at the point. Basically, it's
let's just say that that in this case x is upwards. So if you're in that case, if we're accelerating downwards, then this would be represented by a negative upwards acceleration.
Agreed.
So in that case, we're starting somewhere down here.
No, because that means that you're traveling down, and we're starting from the. Are we starting from the position where you fire out the gun?
Yeah, and in that case, the gravity is going to accelerate it down. That's the opposite direction than your velocity. Therefore, it's
no. You're mixing up. This is the problem. At the point when you have it loaded in your gun, the tennis ball is not moving. You can't say.
All right. So basically,
it's rate of acceleration has to be ball.
So this is basically the acceleration inside the gun barrel, and this is the point where we leave the gun barrel and the gases from the gun are just going anywhere and not really bothering our tennis ball anymore.
Yeah, so you get a quick rate of acceleration, which then levels off, and you end up with 0 acceleration, which would be a horizontal line.
Okay. So where? Down here? Up here? Where is it?
So you've started off where the acceleration point was high. So you've made a triangle, haven't you? So it's the peak of the triangle. That then levels off. So just flatten it off.
Like this? Like an exponential, like this?
So we're looking at the rate of acceleration. So the rate of acceleration would slow to a stop at some point. So you draw in how it would slow to a stop, however you want to do it. It should be easy. It should take it back to the crosshairs, back to the horizontal.
So it's going through there?
Or anywhere.
Like this?
Yeah.
Is it going like this? How is it supposed to go?
Just draw a nice curve so it goes up, curves, and then comes back down.
So like this?
Yeah. So yeah, exactly. That's the rate of it. That's the rate of acceleration from the tennis ball's point of view as it's fired out the cannon or the gun. It goes up quickly, and then it starts to decelerate. So and its rate of acceleration gets less and less.
So it's basically symmetric on the other side.
No,
like this.
No. It's not symmetrical because its rate of acceleration is slow, getting faster and faster and faster.
Or like this. So mirror symmetry, or
no. It would be on the negative side.
So
because it's coming down now, isn't it?
And here, like this.
So, yeah,
like
but the opposite way. The opposite way, wouldn't it? It would start off decelerating slowly, gaining momentum. So its rate of acceleration initially would be slow, but then it accelerates quicker and quicker. So you need to flip it the opposite way.
So, like this?
Yes. Yes, that's what it would do on the way down. It would slowly
and then crash into the ground.
And then it would gain to a point where eventually when it comes to a stop, it would just go, it would flatline and then stop because it hits the ground.
Basically then going back like this and not like that.
Yeah. Do you agree?
Bullshit.
That's what happens. The rate of acceleration, you're talking about the rate of acceleration.
Do you have any kind of physics book from your school days or something else available?
Say again. Do I what?
Do you know what the do you know what the acceleration inside of Earth close to the Earth's ground is? So basically, for the first 100 miles of altitude.
You know what the gravity?
It's 9.81 meters per square seconds. I'm able to tell you that because the acceleration inside on Earth is constant.
So what?
Basically, that means that the acceleration due to gravity does not depend on anything. So instead of this, which is blatantly wrong, your acceleration.
All right, let me screen share on my screen.
Line.
Let me screen share on my screen share, and I'll show you what I mean by, because although you've kind of done it, you haven't done it the way that I really wanted it, but you won't be able to disagree.
I'll share your screen.
Sure. Let's get rid of everything else. I don't know how much of my screen you can see with it being widescreen, but are you still there?
Yeah.
Yes, I'm still there.
Okay. How much of my screen can you see?
Nothing.
You don't see any of my
Apparently
screen?
not screen sharing.
Oh, hang on. Do I need to do that myself?
Yeah. You have to press on the left top side of the window with the Google Hangout.
Oh,
There's
yeah, I see.
Screen share button.
No problem. You're going to see all of it. So what I'll do then is, if you're going to see all of it, I'll make that the whole page. All right. And then I'll draw your lines in. I'll draw them thick so you can see them. And I'll freehand it because this is probably the best way I'm going to be able to do it. Do it. All right, okay. So the rate of acceleration from the point that it fires out the gun, out the cannon or whatever, it goes up very, very quick, begins to crest. And basically, once the acceleration stops, that's where it's at its highest point, there. Then the rate of deceleration would start from there, and it would start to come back down, but it would start slow, and it would begin to get quicker and quicker as it came back down. So that's effectively the rate of acceleration. But because you've got it on this diagram here, let's do it in red. The rate of acceleration will be the same. It would start off fast, and then it would curve to nothing, but then it would have to start here, and then start off slowly and do that. That's what it should be, because you've got the negative value.
I don't think. Wait, give me a second. We can't see it full screen. At least I can't.
Click on his image. Hold on.
Oh yeah, I got it.
Can you see that?
Yep.
So here we have the tennis ball firing out the cannon. Its rate of acceleration is high, but it gradually comes to a point where it no longer accelerates, but it hasn't started coming back down yet. But when it starts decelerating, because this is a negative value, it's two separate graphs effectively, but it has to now start here, and it starts to decelerate slowly, but it gradually gets more momentum so that its rate of acceleration is highest as it hits the ground. And then when it does hit the ground, it all stops for whatever reason, the rate of acceleration stops. So how that's represented...
basically the blue line is your velocity?
No, the blue line would be like
or the altitude.
Position.
If you were to do it in one graph, the blue line would be the acceleration. The acceleration is highest, and then it tails off to nothing, and then it starts to decelerate, and it starts slowly but goes quick towards the end. That's the way it should be. But on your graph, you got it the way you've got your graph set up. I've had to do it on your graph. So basically, it's the same trajectory as the actual flight of the thing. It would go up fast initially, and then tail off, and then come to a point at rest. And then it starts to fall, so it slowly increases its rate, and then it actually gets faster and faster and faster until such time as it stops. So it depends on how you measure which graph you're going to use. But you gave me the crosshairs one, so I've had to use it based on what you gave me. But I don't know how it would be represented in a 4-1, because ultimately its rate of acceleration would tail off to 0. So really, we'll go to the highest point there, but it wouldn't decelerate until it gets to this point. So really, this point is in the middle, really here, but this graph doesn't show it the best. The blue line is the more accurate one. I can't represent it on the quadrant one that you showed. But in any event, the point is, even if you disagree with me, there is a point where the tennis ball gets to 0. There is nothing. There is no forces affecting the tennis ball.
What exactly do you mean by the point of 0?
When the tennis ball gets to its highest point, let me read it. Do it again.
Yep. I mean, which point is the point of 0 that you're talking about? 0 what?
This is the tennis ball in the gun. It gets fired out the gun. Looks. Didn't. Hang on. I copy it. Select. Copy. Paste. Fires out the gun. Gets to its top point, whatever that top point is, and then it comes back down again and it hits the ground.
Mm-hmm.
At some point, it comes to a stop. There is 0 velocity on it. Agreed?
All right, that's what you mean. So the point of 0 velocity.
Yeah, it's in a state where no forces are affecting that pendulum, that ball. Agreed?
Nope.
It has to, because it's not moving. No forces are affecting it.
We had that point already.
Right, all right, well, let's move on.
Accelerated in a way so that it first slows down and then is accelerated the other way back. There's a point on that curve where it's still under acceleration and its velocity is 0.
It's not under any acceleration because its velocity has to... If it was under a state of acceleration, its velocity cannot be 0. It's a contradiction. You can't have it under a state of acceleration. It's under a state of deceleration, I agree, but not acceleration.
That's like saying that my curve is going through the x-axis. So at this point, my curve is going to the 0 point, and as it's moving through the 0 point, it can't have any slope there. You're not even remotely making any sense, Anthony. Sorry to have to break it to you.
No. The bit you don't understand is you're not able to explain it with physics. It's simple. We observe the ball goes high, it stops, it comes back down.
I'm neither able to explain what you just try to tell me with either physics nor logic, nor just basically using my brain. You're not making any sense. Sorry, but Just no.
Just because you don't understand it doesn't mean I'm not making any sense. At some
No,
point,
you're not making any sense because you're not making any sense, and Hector has already told you why exactly you're not making any sense.
the ball goes up, it stops for a while, for a literally a millisecond
For
or
long,
two.
how does it stop?
What?
For long, how do you think is it going to stop?
For how long do I think it's going to stop?
Yep.
Milliseconds. But it has to stop. There's a
It
point
stops
where it's
for exactly 0 seconds.
that means it doesn't stop. A value of 0 means it doesn't happen. We know it stops because it can't not stop, otherwise it continues moving.
Velocity, time. I think I need to zoom in again so you can see it again.
Okay.
If my velocity starts at something high and goes towards something low, for how long is my velocity 0? How long is this point here, Anthony?
Milliseconds.
It's exactly 0 seconds. It's one point in time, and as soon as I move
Hang on.
even the smallest amount of time to the left or the right, I'm even the smallest amount of velocity of 0.
Hang on, you're not representing what we're discussing. You're representing something else. I don't know what that does represent, but it doesn't represent anything else. It would have to flick the other way, wouldn't it?
I can also have it flick the other way. I can also have it flick this way around.
Yeah, but that's the crest wouldn't. It's again, it's the drawing that I drew rather than the drawing that you've drawn. The rate goes up at the beginning, it flattens off, and then it comes back down again. Because
I'm
that's
asking you for how long is that velocity equal 0? How long is the time?
You're not showing at any point there that the velocity is 0. Are you showing what's
All
this?
right, then this is the axis where the velocity is 0. Let's say there's 1, there's -1, there's -1, there's 1. Now you've got it at 0.
So the velocity.
How long is the velocity equal to 0?
Milliseconds.
So if I wait for half a millisecond, the velocity will still not have changed at all.
No, the velocity would begin to change exponentially. It'll go faster and faster and faster.
Is this an exponential curve?
No, and that's why I said it's wrong.
Then why do you say it would change exponentially?
Because that's what it does. The fact that you can't draw the correct curve doesn't mean it doesn't happen. Do you agree that the ball goes up and comes down or not?
Anthony, do me a favor. Open Google and search for how strong is gravity.
No. Just answer the question. Do you agree that the ball goes up and then comes down?
Yes. And that's demonstrating that there's an acceleration at any given point in time.
No, there's no acceleration at the point where it can...
Yes, no, there is, because other way, if there were no acceleration at that point, it would just float at whatever position.
You know what? Let's zoom out a little bit, because it doesn't matter about this. Whether we can agree to disagree on this, because it doesn't change the overall picture. At the state, whether you disagree with me or not on this is irrelevant. Let's move forward. At the point when the pendulum is at its full swing, either at -2 or at +2, the only forces that are affecting the pendulum itself are 0. They're all at 0, unless you allow for the magnetic field, which is now the biggest force affecting the pendulum, because everything else is 0 at that point. Now, you won't agree with that, but that is the only thing that's the biggest force affecting the pendulum when it's at its full movement is well, if it's made of metal, it would be the magnetic force, the magnetic fields, because all other forces are now at 0.
Anthony, I've just put a link in the chat. Would you kindly just open that link for a second and take a look at it?
I got it.
Because that's something that we have to sort out. Because in that case, I think I can show you that in the point that you're about to make a big mistake that's going to negate your whole point.
Really?
Yes.
I suggest that what you're actually trying to do is bullshit me with maths the way that Einstein does.
What
if you
the
don't,
fuck?
If you don't agree that the ball fires up and comes to a stop at some point, and before it comes back down again, then you're in a state of either denial or ignorance, because that is what happens. The fact you can't represent it with physics is not my problem.
Stop. However, at that stop, gravity doesn't just magically vanish.
I agree.
At the link I just showed you in the results tab, there's a point called gravitational acceleration. That 9.819 meters per square second. So that means if I've got something just holding it up and let it go, then for each second it's going to gain 9.819 meters per second of velocity.
Do you know what? I don't disagree with that.
All right. 9.81 meters per square second. That's basically the slope. If we've got velocity in meters per second here and time in seconds, then for 1 second, this is about here, we'll get 9.819 meters per second. That's basically the whole slope thingy.
Right, I'm going to share my screen. We're going to do one graph, and then we're going to move on, because it doesn't matter if we don't agree on this point or not, because this is essentially what the Foucault pendulum is.
I'm feeling that this is going to matter at a later point, but all right.
I don't think it will. Let me open up Paint again. Where's Paint? There we go.
I hope that you're going to be right.
No. Right. So the velocity will have and then we'll have on this one, we'll have time. With the pendulum and with the let's do this in that. Let's make it as far. Right. Right. We'll do you want me to? It is the way I showed it before. Initially, when you fire the ball, the velocity gets high, and then it flattens out, and then the velocity then has a negative value. Oh shit! It's not quite that severe. Velocity goes up, flattens out, and then it gradually goes down that way, but gets stronger as it goes towards the end, and then it stops. So
is that your velocity or your height?
Well, it's both, isn't it? It's the same graph for both.
No, the velocity is completely different.
That would be the height.
First, hold on.
That would be the height, but the velocity starts off fast, flattens out as it loses its velocity, and then the velocity then it's the negative part of the graph before, but the velocity then becomes a negative value as it goes back down, and then it gets bounced to the point where it stops. It's the same graph. Now the reality is you disagree, but that's what we see. Now, if you can't agree that that's what we see and that is represented how I've drawn it, then we can move on, because we don't need to dwell on it. It is irrelevant. The point that I'm making is when the pendulum is at its extremity down there, it's at this point here. There is no movement on it at all. It's in a state of equilibrium. You disagree, and that's fine. But I'm saying that what actually is happening at that point is the biggest force that's being affected by this, or the biggest force affecting this pendulum is likely to be the magnetic forces that we see, because it's the only thing that's not got a value of 0. Everything else's value is 0. You disagree, fine, let's move on, because this ultimately affects the hypothesis.
Well, just 1 second. You said that all the forces on our pendulum have to be zeros. They all have to add up to 0.
Yeah.
Or else it couldn't stop.
Yeah, otherwise it would be in a state of movement, and we know it doesn't move when it gets to the crest.
If it doesn't move, and all the forces are 0, then why is the magnetic force supposed to be not equal to 0?
Because at all times through the experiment, when it's swinging which ways, the magnetic force is always there and it's never counted. The effect of it is, the effect of the magnetic force is... Hang on.
You said if a force is working on it, it's under acceleration, and if it's under acceleration, it can't come to a stop. If the magnetic force were to always work on it, and if a force is working on the pendulum, it can't come to a stop, then why does it come to a stop, Anthony?
Because it loses its velocity. Fucking hell. Right. This is the force of magnetic effect. And this one is the force of time. So as the pendulum swings through its full rotation, so we'll call it one swing, which is from far left to through the middle and far right, this is what's likely to happen. Pen. Where's my pen gone? Right, so the value of magnetism would be, well, in the middle, it would be 0. So it's going to start here. So it's going to go like that. And then you're going to get the full stroke here. And then you're going to get that. That should be equal along the time. These two lines should be equal.
Okay, I get what you want to draw.
So at the point when it's at full swing left, the magnetic effect is highest because everything else affecting the pendulum is 0. But as it gains momentum and it gains velocity, this quickly tails off to nothing because when it's through its stroke, the pendulum's creating its own torque. But then as the pendulum begins to lose its energy at the other end of the swing, the magnetic effect begins to take over and becomes the only force that's affecting it. It should be on line with that. But the magnetic force then would be the only force affecting the pendulum because everything else is 0. So at one point, nothing's happening with the pendulum, with the magnetic force. But
yeah,
when
there's no other force affecting the pendulum, but the magnetic force is still affecting it. If the magnetic force is still affecting the pendulum, how is it going to stop? You said if there's a force acting on it, then it can't come to a stop because it's still accelerating.
Because what happens is the torque that's created by the pendulum when it starts to swing, as the pendulum's doing that, what's happening is that at that point when it's there, the magnetic effect is still present. And it can't affect it because it's magnetic. But the minute it starts swinging, it becomes the weakest force, but it's still there. But there are other forces that are affecting the pendulum until it gets to that point.
So basically, what you've drawn there is the strength of the magnetic effect divided by all the other forces.
Yeah.
So the magnetic effect itself is still constant at all time, but the other forces are much stronger.
Yeah. At that point, there's no other force affecting the pendulum. Other than the magnetism.
Anthony,
but once it starts to swing,
I understood you correctly. What you said before was, in order for the pendulum to come to rest, all forces acting on it have to be 0. Or otherwise it couldn't come to a rest because it would still be accelerating. Correct?
Say that again. Say that again.
You said that basically how I understood you was, in order for the pendulum to actually come to a stop at a certain point, all forces affecting the pendulum have to be 0.
No,
so
the effect of the forces is 0.
All right, so all forces added together are 0.
Yeah.
So you said that when the pendulum is at its outermost position, all other forces are 0, but the magnetism is still there. So the magnetic force, right?
Yeah.
So all other forces are 0. They basically add up to 0. And we've still got the magnetic force that's not being countered. How does the pendulum come to a stop if what you said before is true?
It loses its velocity.
How does it? It loses velocity. But you said it can't get to a velocity of 0 if there are still forces acting on it.
No, I said when it gets to when the velocity equals 0, the effect of the forces that are affecting the pendulum is 0. Because
so in
otherwise
essence, there's nothing accelerating the pendulum in any way.
Yeah. So if nothing,
if there's nothing affecting the pendulum in any way, and also the magnetic effect is cancelled out perfectly by all other forces. If it's cancelled out, why does
the magnetic effect can't be cancelled, can it? The
If the magnetic effect can't be cancelled out, then you've got a remainder of forces that all cancel out, and all that's left is the magnetic effect that's still accelerating the pendulum.
Am I still sharing, or is it on, Hector?
I can still see you.
You can still see me. At that point where the pendulum is at its highest, and it can't go anymore, and it's 0, it's not moving, The only force that's affecting it is magnetic, because the pendulum is magnetic. It's because it's magnetic. It's because it's metallic. As the pendulum starts to move, the other forces that are in play quickly cancel out and cause zero effect. Hence what I've just shown on the map, on the graph. So whilst it's moving like that, it's only as it loses its velocity and it gets up to the point where it's beginning to stop and it comes to a stop, then the magnetic effect is still present, but it's the only force that's acting on the pendulum. The minute it starts moving again, it tails off straight away because of the torque that's created by movement until it stops. And that point, the magnetic effect is still affecting the pendulum, although it's the only force that is, because all other forces are now at zero.
So at the end point there, all other forces are zero, but the magnetic force is still there.
Yeah, the magnetic force is the only force that's in play. It's only when the pendulum starts moving that all the other forces in play, which are velocity, acceleration, gravity, whatever forces you wish, they all then can become the strongest force. So the effect of it, which is why it shows down here, is basically zero, because the torque that's created by the pendulum, its movement itself, overpowers overpowers the magnetic effect. But when it gets to the point where it's no longer swinging and it stops, it's the most powerful force that's on it, because all other forces are having
so
no
you're saying
effect.
there's still a force working on it at the at that very top point that isn't being cancelled out.
And it's the most powerful force, because there are no other all other forces equal zero. So at this point, it is the most powerful force. Even here, it's lost its ability. There, it's lost. There,
yeah, I get it. You don't have to do that swinging thing anymore. I get it. What I don't get is how you can do that without going, oh shit, I just contradicted myself.
Where's the contradiction?
You said before that if there's a force still acting on basically something, it can't come to a position where its velocity is zero. If it comes to a velocity that's equal zero, that means that all other forces there, that all forces acting on it are zero.
What did
and
I
you
say?
just told me that there is still a force acting on it when it's at zero velocity, which is the magnetic force.
No.
Dude.
No. That's not a contradiction. You misunderstood my point.
It is.
It isn't. You've misunderstood my point. All the forces that you've described, gravity...
Dude, I think you just misunderstood yourself.
No, well,
how the hell are you doing that? That's amazing.
You're not understanding my point. That isn't my problem. I understand what you've said. I understand and I agree with you on everything you've said. But the point that you don't get is that when it comes to rest, up in its extreme of its stroke, which is illustrated on screen, all forces affecting the pendulum are zero, but for magnetic effect, because the pendulum is is metallic. The fact that you disagree with that is not my concern. It's your own ignorance. But all forces are affecting the pendulum, which is acceleration, gravity, deceleration, speed, inertia, torsion. All those values are zero because it isn't moving. But at that point, the biggest force affecting the pendulum is magnetic, because all of the forces are zero. If you don't agree, that's fine. But the reality is that is what's happening, because if it wasn't made of a metallic object and it was made of something non-metallic, then the magnetic effect would be zero throughout. But because it's made of magnets, because it's made of metal, it is being affected by because all of I don't know why you don't understand this.
I do understand it. That's the problem. I understood your contradiction.
No, it's not a contradiction. All of the forces, whilst it's up there, are zero. There is no rate of acceleration or deceleration. There is no gravitational effect on it because it's stationary, it's not moving. There is no inertia being caused. There is no torque being created. All physical values are zero. You don't agree.
All physical values are zero. That would be a very interesting thing for the quantum mechanics guys to examine.
Fine. But the reality is it's not fucking moving. So if you don't accept that it's not moving, then your values will have
accept that its velocity is zero at that point. But your point of all other forces being zero is it's not true. Sorry to break it to you, but that's not correct.
The forces affecting the pendulum when it's at that state are zero. Otherwise, it would be moving. Yes, they are.
It is accelerating.
It isn't. It's not moving. It has to be moving if it's accelerating, because that is a change in velocity. But there is no velocity to change. It's at 0. At that point, all of the physical things that you're describing, torque, speed, deceleration, gravity, they all equal 0 because it isn't moving. Now, gravity is there, but it's not affecting it at the moment because it's not moving. So the greatest affecting force that's exhibiting on the pendulum itself is magnetic. That is a fact. You don't agree, but it's true because the pendulum itself is magnetic. It's representing that thing that Alex showed before.
All right. I think in that case, you in reality will have to agree to disagree.
Fine. Thankfully, but we can agree to disagree. But what I'm saying is this is why we're going to get the variation in the thing, which ultimately is the credibility of the Foucault's pendulum experiment itself. Even if it does move, I'll be arguing that it's the effect of the magnetic effect, because at all other points we are in a state of equilibrium. You're going to disagree. But this is why I'm saying if we swing the pendulum north to south, we can negate this completely. So that's why we need to swing it north to south if we can, rather than swinging it at any other orientation. Because if it's east to west...
we just gotta take a weight that's not made of metal.
Or take a weight that's not made of metal. What are you thinking of using?
Fine, in that case, I'm going to take a weight that's not made of metal, do some measurements with it, and then take a weight that's made of metal and see if I see any difference.
And in the same sentence, I'm not blessed. I mean, I'm thinking of using the one at Buxton University, and in that is made of metal, or it's at least tarnished with. I think it's brass, but I might be wrong. It could be some other form of metal, but nonetheless, it is metallic. So I'm going to point it north to south because it is likely to have an effect. But then I'll repeat the experiment east to west and see, do I get different results? But if I do get different results, it only supports what's his face's argument. It only supports Eric Dubé's argument that sometimes they rotate clockwise, sometimes counterclockwise, sometimes they fail to rotate, and sometimes they rotate far too much. It isn't going to prove that magnetism is or isn't having an effect on it, but it does prove that sometimes they do different things.
Actually, that effect was something that I was trying to explain in the beginning with the thing of linear and non-linear systems or differential equations. The thing is, basically what I was trying to tell you was that due to the non-linear nature of a pendulum at larger angles, it can happen that you're going to get the pendulum start to take on a slightly ellipsoidal path. Now, what's done to basically counter that ellipsoidal path is, I'm just going to turn on my video again, is if you've got the, where's my pen again, there. If you've got the pendulum suspended from the ceiling, and it's a rather short pendulum, then what a lot of people do is they build in a metal ring in here, so basically like this, where the pendulum is going through. So at the outer edge of the pendulum, yeah, now you should see it. It's pressing against that ring, going out there with basically an edge in its string and swinging back. And basically, if the pendulum is going perpendicular to the surface of the ring, then all the basically quote-unquote force in that direction is conserved. But any sideways force is subject to a friction on the ring, which is going to slow it down again. This means that if you've got a kind of bad mismatch between swinging frequencies, instead of it, basically, that's the top-down view here. This is the point where we're suspended. This is the inside of the ring, and this is our pendulum. Basically, it can be that if our pendulum is coming in from this way, it touched the ring when it was here, so the ring is held here due to friction. It's going here, then it's swinging there because the string is still held here due to friction with the ring, swinging there and swinging back again. You can basically invert the ellipsoidal path of the pendulum itself, and if you get odd phase mismatches there, the use of that ring, which you need to correct for that ellipsoidal path in rather short pendulums, actually distorts your experiment too much, which is the reason why I didn't want to use such a ring and a short pendulum, but rather a very long pendulum where you don't need that ring to try to cancel out the ellipsoidal path and accidentally end up just fucking up your entire experiment.
All right,
That's one of the possible explanations for that rotational direction thingy. The other possible explanation is you're doing it on the southern hemisphere. And on the southern hemisphere, it's going to rotate the other way around.
Okay, so let's get to the point where we make our hypothesis. What do we think is going to happen when we do it?
I expect to measure somewhere about 10 degrees per hour of rotation in the swinging plane of the pendulum, and probably 1 or 2 centimeters of eccentricity of the path, meaning a very flat trajectory of the ellipsoid.
Now, bear in mind, I'm challenging Dubé and challenging what he said. I don't know what I'm going to get, if I'm honest. I do believe that the Earth, whatever we live on, is not moving, because the gyroscopic tests kind of confirm that scientifically, evidentially. I know you don't necessarily agree with the science behind it, but I believe
I agree with the science behind it. I just think that the measurement method doesn't even remotely provide the accuracy you need.
Yeah, but 12 degrees in an hour is quite a lot.
Again, we talked about that at length. We don't need to repeat that.
But how is the measuring device not accurate enough when it does it, when it's put on a clock mechanism?
If you take a look at the video, at the end of the video, you're going to see the guy rotate the clock mechanism below the gyroscope, in the end also pulling on the wire that he's using to drive the engines, drive the electric motor to just power the gyroscope. That cable, seems rather stiff, and that guy's managing to get the gyroscope to rotate with just that little pull on the cable by, let's say, about 2 degrees per second. That is about 10,000 times as fast as he'd expect it to rotate completely left on its own. The cable and the battery block are laying somewhere on the table, and I think the stiffness of the cable might be more than enough to cancel out any rotation that he should have measured, or that the gyroscope should have done by itself.
But he showed that when the cable was moved, he showed that it did basically exactly the expected rotation that he would expect to see.
Did he upload the video?
Yeah.
Ah, okay. Then please send it to me in the chat so I can take a look at it.
Okay. Can I do that afterwards? I don't want to really look for it right now. We can do it after the event, after the hangout. Or do you want it now?
No, just send it to me now, because I want to get that out of the way right now.
Okay, then. Hang on. I think this is how I found it. Now, that's the guy. No, not him. No, that's not him either. Where is he? Most recent first. His name was John, wasn't it? What was the name of the guy that originally did it? Do you remember the guy's name?
Nope.
John Savage, that's him. Videos. I'll subscribe while I'm here. Right, so copy and go back to Skype. Oh, do you want me to do it in the hangout? It's okay.
No, not necessarily. So
no, I'll do it in the hangout so we've got a record of it. Right, there's the video of him when he removed the wire.
I also found it.
And whilst I'm screen sharing, basically I can show you that he's got rid of the wire at people's request. He's charged it with batteries instead. He's balanced it out. And then as we go,
put the batteries on top of it.
Well, he's put the batteries on the side.
Yeah, basically mounted the batteries along with it.
Yeah, and then basically he shows after X amount of time. I mean, I don't know. You'd have to watch the video and criticize, but basically when he shows at the end of the experiment, there is no movement at all.
Yeah. Now the only thing that's left is test that with the clockwork mechanism,
which he's done. So let me go back to his channel.
I've taken a look at his channel, and I haven't seen him test that with a clockwork mechanism.
He has. Hang on. Bear with me. Let me see if this is the one. Right, that's a sped up version. No, hang on. Is it this one? I think it's this one. I think it's this one. Is it?
Well, basically, he's got one short video and one raw data, and just the raw video material of it rotating working for 1 hour. And yes, we do not see it spinning. Now, the only thing to test is still remaining: is this sensitive enough? That's the whole point of the question.
I know.
So the only thing being left would be to place this construction with the batteries mounted on the gyroscope holder on the clock mechanism and see what happens.
Yeah, he's done that. He's done that. Maybe it wasn't this guy.
He did not do that because he's only uploaded I think it's about 4 videos since you asked him, and those 4 do not include him putting that thing on the clock mechanism.
So I must have the wrong guy then.
Nope, that's the same guy. I recognize his channel.
No,
and recognize the videos he
uploaded. All right. Let me go back to the original evidence. Hang on. Here we go. Just bear with me while I find it. Right. If the gyroscope was not sensitive enough to register the hour hand turning, then the entire gyroscope and gimbal would rotate with the 15°/hour platform.
Yeah, that was the video where the battery assembly and the cable are still on the table, which is what I criticized.
Right. If the gyroscope was not sensitive enough to register the hour hand turning, then the entire gyroscope and gimbal would rotate with the 15°/hour platform. Right. This is the video that you're asking for.
Let it run for a few more seconds, or skip a few seconds to the point.
Should the gyroscope be sensitive enough to register the rotation, then we would see the gimbal move with the platform, but the gyroscope would remain rigid in space and pointing to the same direction it was when it was spun up. Can you see?
Yep, and the cable is still connected to the table.
Oh, right. So,
yeah, that was the one I was criticizing.
Okay, so is this the one that we made the comment on?
I think so.
Or was it the other one? Let's just see if my comment is here.
Either this one or the other one.
Let's just see if I actually didn't, because I can't remember which one it was that we actually left the comment on. But he does address it. Let's do this into date order. Whoa, sit still for fuck's sake. Why is it doing that? Right. So this is on Globebusters, isn't it? So Globebusters are referencing this. So it should be in the links here. For which
we did it on his channel, not on the Globebusters channel.
Okay, so which is the link on here? The original 6-hour gyroscope. Is it that one? 3 minutes summary. It must be this one. Right. So it is John Savage.
Yeah. I think it's this one.
So I've not asked him. I don't think it's this one I've asked him, because this has only had 600 views. And I don't see my comment in here.
Ah, I found it. It's on this video that you made the comment. It's a little bit down. It's the it's from it's the
this video? Which video?
The video I just put in the chat.
Okay, hang on.
You made your comment 1 week ago, and it's the 5th most recent comment. That's the one that we commented on.
Well, is this the same experiment though? Hang on. No, this is the friction in the main bearing one. So we haven't asked that question, but this is the friction in the bearing. We need to ask that question on the other one.
Yes, exactly. Yeah.
Right. So let's
basically the only thing that is that's left there to do is for him to test the setup with just the engine and the batteries all mounted on the gyroscope casing on his clock mechanism.
Hi, John. Great experiment. Could you do the test again, but without the wire?
Or basically ask him on his video, on his newest video with the gyroscope, where he's got the batteries mounted along the engine. Basically the one from 3 days ago.
No, but this is the one that we want him to do it on the one where he's done it on the clock mechanism, right?
Yeah, the problem with this was that the cable might have held the gyroscope in place as the clock mechanism was moving under it, which was why what I would have wanted from him is take the setup that he's got used in his newest video and put that one on the clock mechanism.
Okay, so let's try that. So in his newest video, view videos, newest first. So which is the one that you're on about? This one?
The second newest one. This one.
So this is the one. Right, this is the one that right. This one's not on the clock mechanism though, right?
Exactly, and he'd need to test that one on the clock mechanism, and in the best case scenario, with the clock mechanism once going clockwise and once going counterclockwise.
Can you repeat this experiment like as it is shown in the video, and then I'll put in brackets no wire.
Or batteries on the gyroscope casing.
Yeah. Yeah, because it says as shown in the video, no wire, yeah. But do it on the clock mechanism to illustrate that a.
Oh shit! I'm getting a call.
Okay. To illustrate that a gyroscope can accurately measure the required degrees rotation at your long required degrees rotation at your longitude. I believe you should be able to measure 12 degrees in the UK, so 6 degrees over 30 mins. Any chance you could show this, please? Okay, so it just says, hi John, can you repeat this experiment as shown in the video, no wire, but do it on the clock mechanism to illustrate that a gyroscope can accurately measure the required degrees rotation at your longitude. I believe you should be able to measure 12 degrees in the UK, so 6 degrees over 30 minutes would be enough.
In the UK, depending on where you are, it's I think between 10 and 11.5. I know that 10 is the minimum. I don't know what the maximum is, but yeah.
So should we go with 11 degrees then and say 5.5? I'm not sure where he is.
Then leave that part out because I think in one of his earlier videos he already calculated how much of a rotation he's expecting to measure.
Can you repeat the experiment as it's shown in the video with no wire, but do it on the clock mechanism to illustrate that a gyroscope can accurately measure the required degrees rotation at your longitude? Any chance you could show this, please? Many thanks. Right. So we're going to have to wait for him to get back. But in any event, we can still make the hypothesis of what's going to happen. Because I believe that the gyroscope will show the rotation of the Earth if it does exist, and he'll do it on the clock mechanism to show that it does do it. But he's already shown that in this video that it doesn't measure the rotation of the Earth. So I guess we should wait until he gets back to it. But in any event, we can still prepare to do the experiment. Agreed?
Yeah. While that we can still do the Foucault's pendulum, but still.
So
until I have him proving the manufacturer of the gyroscope wrong, who said that it can't measure that, I'm gonna stick with the manufacturer for that one.
But do you agree that the manufacturer may have tried to measure the rotation of the Earth, and because the Earth isn't rotating, they've said that it isn't sensitive enough to measure it? That doesn't mean.
Or they might have also put it on a clock mechanism and seen if it and taken a look at whether it can measure something that small.
Okay, I'm back.
So let's see what he says then in response. But if he comes back and he shows a video that does the same as what he did before with the wire, then that gives you the scientific knowledge background to make the hypothesis on the Foucault's pendulum, meaning that if the gyroscope fails to record the movement of the Earth or the rotation of the Earth, then the pendulum should also fail to demonstrate the rotation of the Earth. Is that a fair? That's my hypothesis. That's what I think is going to happen. The question is, if the gyroscope doesn't do it and the pendulum doesn't do it the way that it's supposed to, then you're in a position then where physics is going to be in debate, is questionable, yet it's accepted to be the rotation of the Earth proof that proves that the Earth is rotating. But then we'll have two pieces of evidence.
I try to find a way to repeat the gyroscope experiment to check it for myself. Because again, that's only the thing with the cable and the battery pack on the table is one thing that I could see from the video. There might be other things that I can't see in the video that might also affect the experiment. And the only way to know for sure whether something like that can work is to repeat it by myself.
But either way, if we do the Foucault's pendulum experiment and we get erratic or inconsistent results, or indeed it spins the opposite way, that kind of challenges the notion that in some way the Foucault's pendulum proves the rotation of the Earth exactly the way Dubé says.
Dude, before we start analyzing and criticizing and just reviewing the experiments, let's first do the experiments, okay?
Yeah, let's do the experiments. But your hypothesis is that it'll comply with the laws of physics. I am not sure that it will. I'm going to challenge what's his face? Let's get this into the page width. I'm going to challenge Dubé's comments that are highlighted here, because Dubé is the one that's the reason why I'm doing this. And he says that sometimes they rotate clockwise, sometimes they rotate counterclockwise, sometimes they fail to rotate, and sometimes they rotate far too much. This is what effectively I'm testing, and that you're going to prove wrong, and I'm going to see if this proves right. So either way, when we do the experiments, one of us is going to work out, well, we should actually both either fail to verify or we should both verify it. But either way, our two experiments ourselves are going to do something. So whatever they do, it will either support Foucault's pendulum being true, or it won't support it, because we'll both get either different results or we'll both get results that show no rotation at all. If the Earth isn't rotating, I still think the pendulum will move, because I think that it'll create the impression that it is rotating because of the magnetic effect, and I still think it'll present itself to you in a way that will make you support it.
So in other words, you've just opened yourself a backdoor out in case it does rotate to still not accept the Earth is rotating.
No, but it has to do it at the degree for me to accept it. It has to do it at the rate that you, or at least close to it, that you've calculated that it should do. So for me, it's did you say it was 12 degrees? So it's 6 degrees in half an hour.
For you, I calculated. I think it was 10.5 degrees
in an hour.
In an hour.
So 5 degrees then. If it shows 5 degrees rotation, then I will say that does support the rotation of the Earth. But if it shows,
hold on. I'm wrong. It's 12.107 degrees per hour.
So that's 6 degrees. So
yeah,
I will
exactly. So you were wrong. You were right in the beginning. I was wrong.
Just hang on one sec. Hold the line 1 sec, because something's going to happen. Just give me 2 minutes and I'll be back.
Yeah, sure.
Hmm.
Okay, I'm back. I'm not giving myself a backdoor out. If it shows 6 degrees plus or minus a degree, I'll accept that. If it shows 2 or 3 degrees, then I won't be accepting that, because there are other things that can cause that, and it doesn't support the idea of the pendulum being the absolute proof that it's claimed to be. So it has to be relatively accurate, plus or minus a degree. Otherwise, it's not reliable. Is that a fair comment that you'll accept? Hector?
Hector?
I think he's going for a drink.
Maybe.
All right, I'm back. I took a short bathroom break.
Yeah, no, it's okay. I was just saying that I will
Well,
accept.
for me, it's going to be 5.5 something degrees that I expect.
If we do the experiment and we get plus or minus a degree, either way, I'll accept that as satisfactory in rotating the Earth. I'll give it a degree either way of, things like opening doors or people moving by it, creating a slight downward draft or an upward draft or whatever.
In order to correct for that, I'm planning to do multiple experiments, because if people do that, then the errors should be totally random. So some should increase the speed of rotation, some are going to decrease it.
Exactly. You should do the experiment at least 10 or 15 times or so.
Alex, I'm explaining. I'm going to do the experiment a few times, calculate the average of all the values that I measured, and then calculate the deviation, the average of the deviation of my individual experiments from the average. This way, I can get. This way, you can get a rather good estimate on how accurate your experiment is.
But you will show all your values, the raw values, won't you? You won't.
Yeah, sure. I'm going to show raw data. I'm going to show the measurement, the calculations I did on that raw data, and so on.
So basically, what you're saying is, if you get erratic results, then that doesn't disprove the Foucault's pendulum as evidence to prove the rotation of the Earth. Is that what you're saying?
It depends on what you mean by erratic. I mean, if one is going to show 12 degrees per hour, one's showing 10 degrees per hour, then it's not going to be as accurate as I had hoped, but it's still going to be kind of accurate. But one's showing, let's say, 50 degrees per hour and the other's showing -10, then I obviously did something really wrong, and let's apply. Either scrap my experiment or just try to repeat it in a way.
Can we denote where we would draw the line between erratic and acceptable in terms of your position and your longitude? Because if you're expecting to get, did you say it was 9 degrees in an hour? Is that what you said?
I'm expecting 11.398 degrees per hour.
So should we do it over half an hour rather? Because an hour is a long time to sit and watch. Can we agree that we'll do half hour?
Dude, you've got no idea how long other measurements take. The LHC measurements took about a few months until you've got enough data. So I'm ready to sacrifice 1 or 2 days for this, just to be accurate enough.
Yeah, but I'm not blessed with that ability, am I? Because I'm in a university hall, unless I manually recreate it somewhere else.
Yeah, in that case, I don't know. And as long as you do 2 or 3 measurements, you're at least going to get some estimate on how accurate you are. Well, and I think for that half an hour might be enough. But in that case, if your measurement is off by 1 degree and you're expecting to measure 6 degrees, then you're between 5 and 7. If I'm gonna wait 1.5 hours, I'm getting 18 degrees. So So if I have a 1 degree inaccuracy, I'm going to be between 17 and 19, which is a lot less relative inaccuracy. So yeah, of course, it's fine if you do it for only half an hour instead of 1 or 1.5 hours, but in turn you settle for a lower accuracy. You got to be aware of that.
So plus or minus 1 degree would be acceptable. Is that a fair comment? Is that a fair?
Let me think about it.
I would agree with plus or minus 1.
I'm not certain if that's enough of an inaccuracy, because there's a lot of things that can push that thing off. I'd have to know a little bit more about how the pendulum is exactly set up in order to know that.
You mean my pendulum?
Exactly.
I'm not even sure I would know that, and I'll be there. I mean, right, I'm going to say...
You know what? Just take a lot of photos of just about everything around, off and around that pendulum that you can get, and send them to me, and I'll take a look at them.
What I'm going to say is that I'm planning on doing 2 30-minute tests, because I'm not going to have all day, but I think they'll let me have an hour. So if I do 2 30-minute tests, one of which is facing north to south and one that's facing east to west, I'm expecting that the one that's east to west to give me a bigger distance away from what I'm expecting. In my case, it would be 6 degrees. I'm expecting that to be like outside of plus or minus 1. Whereas if I do it north to south, I think it'll be within plus or minus 1 degree. Because I think that there is an effect that magnetism is likely to have on it. I know you disagree, but if it's illustrated by doing 2 tests at half an hour, that kind of does support it. So that's what I'm planning on doing. Unless you ask me to do it like just both north to south, in which case north to south will just verify up.
In that case, I think it would be best if you had a way of taking a pendulum that's non-magnetic, just to rule that out, and do your experiments in one direction, because essentially what you're doing is you're doing one measurement for one direction, one measurement for the other direction.
I agree.
And one of them is 2 degrees too fast, and the other is 2 degrees too slow. It might be that those 2 degrees are a random error that you got from people walking around or other things, and you might falsely think that you're correct on something.
Agreed. But you
one of the big things that a big problem with is, as I said before, and I think it was Skype, any measurement result without any inaccuracy given is worthless in physics. You got to know how accurate.
No, I agree. But I know, but don't
that's
forget, this isn't my pendulum. This is
I know.
This is the column.
In an ideal case, you'd have about 5 measurements or so, all with exactly the same initial conditions, so that we can basically do an error calculations on them and see how accurate this is.
What I'll do then is I'll have to use the magnetic one, but to negate the potential of magnetic interference, I'll do it north to south, and I'll do it twice. So we should get similar results both times.
Yeah. Or basically just repeating the experiment in exactly the same way.
Yeah. And then you do your experiment, and to do the same thing, would you do it for at least 30 minutes and do it north to south if you can? Mind you, you're not
I'll do it for as long as the pendulum doesn't hit anything in the staircase, and I'll.
Is your staircase square or is it rectangular?
It's rectangular, so I've got a limited area that I can do it, and I can examine any difference between north, south, and east, west. I've only got a fixed east, west direction. So I'm going to do it one. I hope I'll find a non-magnetic pendulum. Probably just a bucket where I removed the handle and replaced it with fishing line.
The handle would be metal, wouldn't it? The handle would be metal, wouldn't it?
Yeah, just get rid of everything and then use a metal weight. And
no, don't use metal weight.
Once with a handle, once with a non-metallic weight, once with a metallic weight, to see if that makes any difference.
Yeah, but if it's got a metal handle, that might influence it if there is.
Yeah, of course. That's why I'm saying I'll remove that and just see if I can suspend it with the fishing line.
Or just use a fully plastic bucket.
Yeah, of course, fully plastic bucket and filled with a bag of sand.
Yeah, I mean, we both agree that the weight of the pendulum's not really that important. What would be interesting is what my length of wire is compared to your length of wire.
I can calculate that if you take a video or just measure the time it takes for the pendulum to swing back and forth exactly once.
Okay.
I can from that I can calculate the length of the string. Oh, and if you've got the means to measure it, you might also want to measure the basically eccentricity. So how far left and right from the center point your pendulum is going back and forth at the end of your measurement. It's not going to be that relevant for the measurement of the Earth's rotation itself. However, it's data that we could get our hands on, and if we can get our hands on it, better to get the data and not need it than the other way around.
So you mean as it passes through its center of swing, you want to know the width of the swing?
Oh, just hold on a second, Anthony. My dad's asking me something. All right, I'm back. It was just some questions regarding dinner.
Just hang on one sec. Give me 2 secs.
I think we have to stop this hangout for now. We're already at 4 hours.
Yeah, it's okay. Well, ultimately, the bottom
Only
line
4
is
hours?
Yeah, it's only 4 hours. It felt like 20.
The bottom line is we need to do the experiments, see what the results are, and then extrapolate from the results what we conclude.
Yeah.
And if we do the experiment, if you're going to do it with a non-metallic one, and I'm going to be stuck with a metallic one, then I'll do it north to south if I can, if they let me. But we'll just record it the way we can. The only thing I was going to ask you is how will I don't know what the setup is exactly, so I don't know how I'm going to measure the movement from. I don't know how I'm going to measure it because I don't know what I'm going to get when I get there. So I don't know how I'm going
If the
to.
pendulum is rather close to the ground, what you can do is take a roll of duct tape and some pieces of paper, and if you pull it to one side and let it go, tape a piece of paper on the ground from where you're letting it go, and a piece of paper on the ground on the other side, and then mark the position, the initial positions of your pendulum with a pen. Make a mark after, let's say, and then make a mark after 30 minutes, and reset the pendulum and do it again.
But how would I know where to put the mark? Because is the mark going to be based on my perception of where it appears, or is it going to be based on
below the pendulum? Basically, it's going to be fine if you just position yourself exactly behind the pendulum, so that it's going to be just straight away from you, and you're not going to see any movement left or right. And then put the mark down it so that it's below the vertical line of below the string that the pendulum is suspended from. So basically, the line has to be exactly below the pendulum.
Yeah, but that's what I'm asking. How do I get that exact point below the pendulum if I'm going to be doing it by eye?
In that case, you might probably ask the guys from the university if they've got any idea how to accurately measure it. Because my first idea would be just, have a piece of paper on the ground where you're going to mark everything. If the pendulum is a big distance above the ground, then things are going to get interesting.
Well, what I was going to suggest, I was thinking maybe like a coat stand, a freestanding coat stand that gives you a vertical.
Yeah, you could also just place something behind the pendulum from where you're letting it go and mark on it where the pendulum used to be. Yeah, in that case, it's going to be interesting with measuring the angle, because after all, you're only measuring 6 point something degrees.
Yeah, but
that's not a lot.
Depending on how big the swing actually is, the bigger the swing, although it's still 5 degrees or 6 degrees, it's going to manifest itself with a bigger circumferential distance.
Yeah, so for 5 degrees, you've got about 5. Hold on, pocket calculator.
It depends on the size of the radius, though, doesn't it? The bigger the radius or the bigger the diameter, you're going to get an arc.
Where's that stupid thing? You've got 6 degrees sine of that. You'll basically have for a radius of for an angle of 6 degrees, you're going to be 1 centimeter to the left or right for every 10 centimeters of distance of the pendulum to the center.
So if you
pull it 1 meter out, you should expect about 10 centimeters of travel time
per degree.
For your entire 30 minutes measurement.
So 10 centimeters. So but if I did say I got a hat stand and then I started the pendulum swinging, and then I put the hat stand, allowing for a reduction in the momentum of the swing size, because it's going to lose energy as time goes by. So it'll be a little bit in front of it.
No. Let whatever you're putting on the ground stay where it is. Don't move it. And after the 30 minutes, try to find a position from where you can look at the pendulum, and it's only moving back and forth and not to the left or right of you. And also take a look at the vertical line and try to find that position. I think that's probably going to be the most accurate way.
Well, what I was considering doing was if I took a hat stand and then standing that at the point at the beginning where it starts to, it's just literally almost touching it, and then take a tape measure and then show the distance at the end of the experiment where it's now hopefully moved, then I could measure it to the point where it's almost touching it, and then that'll give me roughly the circumferential distance that it's traveled. If you had that distance, would you then be able to calculate how much it's moved?
Yeah, but one thing that you gotta watch out for is the pendulum is due to friction with the air. The pendulum is most likely going to lose a little bit of energy, therefore not swing out as far.
Yeah. That's why I was saying to allow for the reduction in momentum.
Exactly. So what I'm going to need is the distance between the resting point of the pendulum and basically the position where you're measuring the distance between this is where I started it, this is where it ended up, and the distance between it started there and there it ended up.
Yeah, I agree. So if it's at rest, once I get it at rest, I can pull the pendulum back, put the hat stand, that'll give me my vertical point of reference, let it swing, and then by the end of the experiment, just show the tape measure with how many centimeters it's rotated if it's rotated. And then we can use that based on the radius size and based on the movement. Then we can calculate how. Is that all I need? With all that, just them two information, you can calculate the rest.
Yeah. But basically you have to watch out that you're. Hold on. Let me turn on my camera. Basically, if pen. Where did I put it? There. If this is the central point. This is the initial position, and this is the final position.
Yeah.
I need this distance.
The radius of the circle.
Yeah, the radius, the distance, and one thing you have to watch out is at the end it's probably not going to be moving out there, but just out there. And what you can do is measure this distance and that angle. That's something I can work with. Or you can measure the radius and the basically projected distance to the outside with a 90-degree angle in here. Either of those will do. Watch out which one of those it is. And in this case, you also have to watch out to measure that angle rather accurately.
Yeah, I can't measure the angle accurately, but what I could do is I could measure it with the other, when you said at 90 degrees, when it's...
Yeah, you can basically measure R and D.
Now, can we just confirm which way it's supposed to rotate? Is the rotation clockwise or counterclockwise?
Hold on, let me think for a second. Sun's rising in the east.
It's going to be. It's going to be
So it's
counterclockwise.
The Earth is rotating counterclockwise below us. So I think we should expect a clockwise rotation, as the Earth below us is rotating counterclockwise. So basically, we all are rotating counterclockwise, watching a stationary pendulum. So to us, it's going to look like the pendulum is rotating clockwise.
Do you mean clockwise from above, or do you mean clockwise?
Clockwise as seen from everyone standing around it.
So if that is the case, the clockwise would be... So it's going to move to the left? Is that what you're saying?
Yes. I think.
I agree. It's going to move to the left from our perspective.
Yeah.
Okay.
I think that's right. But I'll contact you if I get another idea why that might be wrong.
Okay, that's great. So let's
much
wrap
thinking
it up.
about deeper theory that I haven't even thought about which way it's supposed to rotate. God damn it, Hector.
Yeah, that's okay, because it's confusing, because it's just the way it is. It's confusing, but it's going to go left.
Yeah.
Right. I've got a call. I'm going to have to go. So let's wrap it up, and we'll conclude after the results.
All right. Bye.
Okay.
Bye-bye for now.
Bye.
Bye.
So what I'm going to do now, as usual... Hector, did you leave? Okay. What I'm going to do now, as usual, is I'll open the Hangout for the live chat. So give me a second. This is so tiring. Okay, Hector won't be able to join. So here we have the link. Hallo Hector.
Hallo. Lange Diskussion.
Ja.
Wieder mal ein paar Teile, wo es deutliche Meinungsunterschiede zwischen Anthony und der Realität gab. Und ja.
Hector, wir sind immer noch online.
Ja.
Hello everybody.
Hello.
Hello. I'm Mariah. Hi. Long time no see.
It wasn't that long. We saw each other last week, I think.
Yeah, it's under a week ago.
So, your opinion?
I keep being amazed just how little of the world he actually understands.
On like you had a hangout with Riley or something again?
Yes.
Yeah. Well, I didn't say much during the hangout because this is Hector's topic.
Yeah, it's
We're
physics.
talking about pendulums. So
I haven't watched it yet.
Don't.
It's 4 hours.
Yeah. Well, the first 20 minutes or so are actually entertaining because we had Reds in the hangout. So yeah, that was something.
And Anthony, yeah.
Yeah, the point, did you notice he doesn't understand that a non-moving object can experience an acceleration?
Yeah, he simply didn't grasp that.
The difference between a point in time and a certain amount of time.
Yeah, he apparently thinks a point can be flat, whatever the fuck that means.
The thing was, he thought that. Hold on, reception might break up for a second.
No, I know what he thought, but like he's at one point said that the point where it crosses, where it crossed to 0, that's flat. That doesn't make any sense. You can't have one point be flat.
Yeah, it's. I tried to explain it long enough to him. I'm not going to explain that again.
Also, I think he doesn't understand that there's not like deceleration isn't a thing. That's just an acceleration in the opposite direction.
But
basically, in physics, when you're talking about a movement, you're also talking about a direction. And if something is happening in the opposite direction, you're saying, okay, it's happening in this direction of the movement, just with a negative amplitude to denote the negative, the backwards direction.
Yes.
And basically, if you don't do that, you're making your math artificially difficult. And I don't mean like just minor difficult, but just no, you do not want to do that.
yeah, I'm not too good with physics.
Dude, no problem. I can teach you a few things. I like doing that.
Oh no, not more. Hector, today I can't take anymore. Sorry.
Hey, you don't need to watch it.
I'm the guy who's hosting the hangout.
Just turn on your speakers.
It also doesn't have to be in the hangout.
Yeah, whatever.
There's a difference though. Like, okay, I don't know much about physics, but if I look it up, I will know said thing about physics.
Yeah, you're not dumb enough to pretend to understand things you don't understand.
Yeah.
Well, again, the problem with Anthony isn't that he's that he's been taught a few things that just aren't correct. The problem is that he's refusing to acknowledge if I show him something that should make him go, oh right, that was wrong, so this is correct. It's just it can be frustrating.
Can be.
Well, of course, the difference between me and a lot of people is I know I'm an idiot, and I am willing to accept that I'm an idiot. And
dude, it's not like I can change that.
Can confirm.
But I like being an idiot.
Yeah, but you're a different kind of idiot, because the fact that you know that you're an idiot means that you're not really an idiot.
Well, fair enough. Which reminds me, I have to grab my lasagna out of the oven.
How did that remind you of that?
Damn you! Now I'm hungry.
Well, I was looking at the clock, and that's actually what reminded me about.
Okay.
Be right back.
I think you're going to be here in between about 20 minutes because I definitely need to get something to eat.
Does it help if I say I just had chicken legs with rice and barbecue sauce?
No.
All right, screw you guys. I'm AFK for 20 minutes. I'm going to get something to eat. See you later.
See you.
I'm gonna be making tomorrow. I'm planning to make Mexican pancakes, but in a barbecue version, because I have plenty of barbecue sauce left over.
Nice.
Mm.
But then we shifted a topic from Anthony Riley to food.
I think that's a defense mechanism.
Probably.
I watched the Pyramid Hangout.
Oh no!
Why would you do that?
So I wonder if an insanity plea would actually stick if I murdered someone while listening to it.
There's a good chance, although I don't think you could. I think you would have a hard time bringing it up as evidence in court, because in order for that you would have to show the people in the courtroom that hangout, and they would become insane too, and be unable and so wouldn't legally be able to actually pass a judgment on you.
You know the really annoying thing? My boss in university just sent me a version of a protocol he wants me to correct. And basically, he and I were using different programs for quotation. I'm using EndNote and he's using BibTeX. So all I'm going to do in the next 8 hours is convert his quotations from one script to the other.
Oh.
Are there no automatic transcoders for it?
Yeah.
There might be, but I don't have the software here. If they are somewhere, then they are in the university. I don't have them. The fun thing is, I started 4 hours ago during the hangout, and I now have 12 or so, and it's about 80. So that will take the entire night, probably.
Have fun.
In that time, it would probably be faster to make the code yourself.
What I was doing, because it's literally faster to research the papers he's quoting and download it again for the matching format.
Well, have fun. I will be thinking of you when I will be raiding in 45 minutes.
Okay.
Hey, gotta love World of Warcraft.
No, you don't.
What? Because of the EVE Online Hellseye?
Maybe. I'm totally not biased.
No, I gotta admit, EVE Online is better, but I stopped playing it.
Yeah, same.
Yeah, I think I'm going to do maybe half of it today and half of it tomorrow.
No, you will do it all now, and you will like it.
I'm fairly certain it's not possible for you to do it all today, since there is.
Yeah. No, you know what I mean.
He will do it all in one sitting, and he will like it.
No, I can't. I'm out of caffeine.
You will do it right now, or you will have a hot date with Riley.
Oh God, I don't know which is worse.
I don't think that. Well, that's an empty threat, because it's impossible to have a hot date with him.
Can you imagine the small talk? Like, okay, so by his usual rhetoric, it would be, sorry, that's not what I talked about. So let's agree to disagree and move on to the next topic.
Yeah, I mean, one thing that he seems to be doing is that whenever we explain something in great detail to him, he'll shift the topic and say that we can't agree for some reason.
He'll just dismiss it.
Yeah, exactly.
Like, and the more specific the explanation gets, the more desperate he becomes to just moving topic.
I'm really looking forward to what his probably very long video regarding the 20 minutes or so he was talking to Red.
Well, I didn't listen. I came in just before the 2-hour mark because
Let me tell you the story. So in the beginning,
God created the universe.
No, that didn't happen. We all know that. So in the beginning,
everyone knows this universe creating pixies.
So Hector was talking with Anthony about the Foucault pendulum, and he agreed that he would do the experiment. Then for some reason, Anthony also challenged Red if he would do it as well. So Red said to me, probably, maybe, but he would like to have a conversation with Anthony first. So I didn't know at any point if Red would do it or if not. So we set this up, and then we had a really weird conversation between the two.
Well, no, it wasn't really weird. It was just that Anthony didn't actually want to answer any of Red's questions.
Yeah, but
let me guess.
Justified in that way that this wasn't really planned for the hangout.
Let me guess how it went. Anthony would claim something. Red will ask him to clarify. He would attempt to clarify. That never happened. Red dismissed his argument by actually providing evidence to the contrary, and he would just say, "I don't believe you."
I think they didn't really come up to arguments. It was just
they did basically like because Riley made like a 20-30 minute long video about Red's short appearance in Sean Hopper's hangout, the one about Jism.
Oh, okay,
yeah. Like
when they called in from work.
Yeah. He had a short rant about how it's ridiculous, like the whole people who use the scientific methods of pedophiles thing. He had a rant about that.
Yeah, I have no idea where that connection is, but
yeah. And then Riley decided to take that part of that hangout and go through it, and he's basically in it. He basically accuses Red of like because Red in it he says, he's done all the things that the flat earthers has asked him to. He's gotten the fucking cameras. He's done the experiments with the boat over the horizon and so on and so on. And they still don't accept it. And Riley basically disagrees with that. He thinks that Red hasn't done what he has, all the things he has to. He's been asked to do, which is why he challenged him to the pendulum thing. But he didn't.
Literal hours of specifically made videos on his channel that I've participated in, they do not exist.
Not necessarily that they do not exist, but they first of all don't prove anything for some reason, and that they are not the answer to the question that Riley asked or something.
And basically, what Red came in and asked is because Red was like, "No, I don't need to watch. I don't want to watch 30 minutes of you rambling on. Just tell me the main point, and how that relates to the." And what Riley has to do with the whole pedophilia thing, and Riley basically didn't want to give him an answer.
Oh, well, that tends to work out well when you don't want to answer a question.
Well, to be fair, I think Riley and Red had different ideas of what this hangout was supposed to be.
Yeah, that might be my fault, but as far as I understood it, Red, prior to the debate or the hangout, didn't say that he wouldn't do the experiment. So I thought that he would come in here and hear what Riley would demand, and then maybe do it or maybe not.
Well, it's so. Does anyone know offhand, like how long does the pendulum arm actually have to be to give a decent result? Because I don't think it's possible for all people anywhere to build it necessarily. Like if you, so especially where I think Red lives in a one story tall house, and doing it outside isn't necessarily feasible.
Yeah, I think what is always recommended is a height of about 10 meters.
Yeah.
And basically, the higher the better.
Well, yeah, obviously.
Yeah, for various reasons. First of all, the period is higher. Second of all, the angular difference is actually higher at the... So you see it better. Let's say just like that. So yeah. And yeah, there's actually, when you have a longer pendulum, there's actually less air resistance.
What for experiment are we talking about? Like about the rotation of the Earth or something?
Yes. Yes.
Yeah.
So you have a pendulum, and the plane in which the pendulum is swinging is rotating because of the rotation of the Earth.
So it's like changes a few degrees, like every this amount of minutes.
Yeah, it's about 10 degrees every hour.
Some shit. What was the relation there? Like it depends. So the degree of rotation per hour depends on the latitude, right?
Yeah, the closer you are to the north or south pole, the better it is.
Yeah. So
there's no rotation noticeable on the equator.
So essentially, I would probably be one of the ideal candidates, being at 61 degrees.
Oh yeah, 61. Oh, where are you in Norway? Maybe.
Yeah.
Oh, okay. 61.
Yeah. I could probably do it here in the Netherlands as well. I mean, you guys could probably do it in Germany.
We are doing it in Germany.
Well, there you go.
The only
back in the day, like there was this program on television here in the Netherlands. It was called Domino Day, right?
Yeah, I know it.
they actually use like pendulums for like the let's say
for the commercial breaks. Yeah, I remember.
Yes, and they would use that because they actually calculate like, okay, this amount of time we need that pendulum to swing, so it takes the next domino brick, so it can continue. It was pretty nifty to see.
So the only problem is I can't necessarily do it at home, but where I work has multiple. Well, let's just call them warehouses. They're essentially garages / mechanic shops thingies with about 10 or 12 meter tall roof space. And when I work nights, they're empty.
just give me a second. Riley just sent me a message that you both are invited to do the experiment.
Oh, I can probably. I just need to makeshift something that I can attach to the roof of some shit, and I can even make it out of something that's not magnetic, since that apparently was an objection.
You know what would be really awesome for that? The inside of a wind turbine.
Isn't that like obstructed with a ladder?
Not necessarily.
Fair enough. Well, you could probably just rent like a sport hall or something for like let's say an hour or two.
Probably, yeah.
So, like I said,
expensive.
I have access to warehouses, or like essentially they're what's the English word for it?
I'm saying in Norwegian. I might.
It's
Workshop.
Yeah, but it's like it's for vehicles like trucks.
A garage.
And like
garage
excavators and shit. Yeah, it's essentially a workshop, but it's like I think the roof height is around 10 or 12 meters.
Awesome. By the way, I already have a template for the scale. I can show it. Give me a second.
Make the shit out of wood and string.
Yeah, sure. not the pendulum itself, but the scale we will attach underneath the pendulum to measure the shift.
Yeah.
So.
Well, it sounds all fun and dandy, but I'm not gonna do this shit because I'm broke and I don't want to spend any money on like wire.
Can you see my monitor?
Yeah.
Yeah.
Oh, by the way, this here is the shit that I have to do. This is one of five or so. And
do I see macaroni?
So no. So this is the old format. This is the new one here. And during the hangout, I could do those and another set. It's so annoying, but whatever.
Ugh.
So
all I see is a lot of chemistry shit, and I'm essentially chemically illiterate. So
I saw some nice hexagonal rings.
Yeah,
Which probably means it has I'm guessing it has some kind of smell to it.
This stuff really hasn't. It's more or less it's hydrocarbon. It's a solid. And usually they don't smell very much, at least at that state.
I think when it comes to any scientific field, I think the one I know practically zero about is its chemistry, like pure actual working chemistry.
Yes.
Just because it's so fucking complex.
Well, so I'm just scientifically illiterate, so we got that to go.
So we've got this nice scale with 1 degree difference. That should do it. And 20 degrees maximum. We should calculate the amount of change we should see for the 61 degrees north, because that would be awesome. You will have the best possibility of us to do it.
I can see if I can make something. Because when I work nights, I'm usually the last one to go, and no one's there when I start the shift even. So I essentially have the entire place for myself.
Nice.
So, do you guys know something scientific about lasagna?
Yeah, it's delicious.
Fair enough.
That is a scientific fact.
Yeah.
You probably find traces of horse meat in it.
Especially if you buy it from IKEA.
I don't think IKEA sells lasagna. It sells shitballer.
They do here.
No, lasagna is my favorite food.
What are you, Garfield?
You could say like it's cake with meat. Who doesn't love
Cake with meat.
Yeah, who doesn't love cake with meat?
I mean, it kind of is.
Well, I mean,
it's cake made out of
meat and cheese.
Yeah.
it has everything you would ever need. It has meat, cheese, and pasta, or some form of
vegetables.
pasta. Well,
I'm fairly certain you wouldn't be able to live off of lasagna. There's probably something in it that you wouldn't get enough of.
probably.
Well,
I think
I've been living on this shit for like a month.
I know I've read it. I'm not entirely sure exactly how true it is, but I know I've read that pizza is one of the food types you could live off of exclusively. Oh, granted, it can't be any pizza, right? It still needs to be a pizza that has vegetables and proteins on it. But
Yeah,
Well,
I
it's
just
gonna
read-
have
it's read-
vegetable. It's
I
gonna have
just read that
vegetable.
you can do the same with only potatoes and butter.
really?
Yeah, it said
That,
that.
that sounds even more unlikely. I mean, because
Probably.
that's just fat, protein, and starch.
Well,
It's not like potato is basically just starch and water.
butter has a shitload of vitamins in it, though,
That is true.
and so does tomato.
I mean,
Well-
because actually, anything that has a milk product in it is gonna be
It's gonna have
be a
vitamin
good.
like D and
Yeah, it's gonna be a good bet because that's comes from something that's meant to keep something alive where it's its only diet.
Well,
yeah.
if you have to believe anywhere, you can believe you can survive on Mars on only potatoes and Vicodin. So
Well, to be fair, he wasn't he wasn't on Mars that long enough to actually start getting deficiencies.
No, and he still had the food reserves that was meant for
Yeah.
the entire crew, so he
Well,
could supplement it.
well,
But the main diet was potatoes.
if you have to believe the books, at least like at the end of like the book, he
So-
had like 40 potatoes left.
He actually, so the author actually got interviewed, I believe it was on Star Talk Radio with Neil deGrasse Tyson,
I think
where he actually talked about specifically why it is potatoes, because he, I believe he said he originally intended it to be beans, but there were I don't remember specifically what he said, but I think he ended up swapping it to potatoes because I think they're easier to grow and they can be used as supplements for more types of meals, just for diversity for the crew.
and they would probably have an easier time growing on Mars because they like potatoes, for those who don't know, are grown in like usually in sandy soil that hasn't got that much nutrients in it.
Yeah.
Well, if you like read the book, he actually talks about beans and stuff like that in the book as well. So like, if you think about, he could actually grow those beans and the potatoes, and thus have a more varied meal, I guess. Beans.
Beans and potatoes would probably make a very stable diet as well.
Yeah.
Just for the pure nutrients. Like just it wouldn't be tasty over a long period of time. But
I mean, you would definitely get enough macronutrients. I'm not entirely sure about micronutrients.
All right, I'm back. What did I miss?
I'm not entirely sure, like the content of potatoes and beans in that regard.
Believe it or not, we're still talking food.
well, to be fair, we have been around other topics.
Yeah.
Yes, but I like how we're still talking food when he comes back.
Yeah.
Oh, hey, we gotta make him hungry.
He's probably stuffed his face.
Well, not with lasagna. That's what I did.
I think at this point you have a lasagna addiction.
So, Micro, I think we've found our way to become billionaires here, Micro. Let's start the first pizza franchise on Mars.
And who will we be selling to?
Well, see, it's a long con, right?
You don't fucking say.
We will be selling it to Mark Watney.
To be honest, your customer base isn't going to be that big with a pizzeria on Mars.
They're also
Hey,
not gonna be
hey now.
particularly picky.
Everyone knows, right? So after you've eaten pizza, you fuck. So, multiplying, you make your own. Make your own customer base.
By that logic, I should be having sex every Saturday because I eat pizza every Saturday.
Well, you're a loss, I guess.
I've been doing this whole time, and I didn't know I was supposed to fuck afterwards. Damn.
Yeah.
You know what I'm gonna make? I'm going to make a pizza with lasagna on top.
Oh god. Also known as the artery clogger.
Yes.
That's not really gonna clog your arteries that bad.
Well,
I mean, it depends how much you will eat of it.
The whole pizza.
There isn't really that
The only correct answer
be
to
that
that
bad
is
for
until you're out.
cholesterol. Oh, like
Well,
if
I actually should take a cholesterol measurement someday. Like I've been eating unhealthy for the last 11, 12 years.
But it depends a lot on how you've been eating unhealthy. The problem is the thing is a cholesterol test doesn't actually test cholesterol.
I have lived on
it's a very, very indirect test. That's
micro. I've lived on pizza, lasagna, and macaroni for the last what? I'm not 28. Well, let's say.
So you've been eating Italian.
12 to 13 years, if not.
That's all Italian foods.
12 years. I've been living on lasagna, pizza, and macaroni.
Now, see,
Wait.
but by those types of food only, wouldn't you technically be more in danger of, depending on how you eat, diabetes than having?
Yeah, I would be more worried about diabetes than atherosclerosis.
I'm healthy as a horse. In IKEA.
Now I have the image of a live horse walking around in IKEA, like between the furniture.
There needs to be a commercial.
Don't eat me, bro.
Either that, or it's got a giant tag with Pferd on it.
Also, you gotta Photoshop that for me. A horse in IKEA with the text "Don't eat me, bro." You have to do.
I mean, that could be an IKEA ad actually, like just a horse going around sticking its head in like the different in the closets, and I can see that being a successful series of commercials.
1980s.
If they did that, it would actually be a good way to laugh a little bit about their own mistakes in the past.
Yeah, that too. Okay, I heard Gio say 1987 or something like that.
Yeah, I'm already again browsing the different references, and there's some inconsistency for some reason.
I thought you were wondering. I thought you were gasping over how old it was.
No.
Because then I was going to say it in my bachelor's thesis. I had something from the 1800s.
Interesting.
Oh yeah, that's true. I'm in a room with smarty people now.
Well,
actually, guys, I might after these 4 hours, I might be in need of some minor therapy. Would you mind if I just abused you and told you a little bit about physics properly this time?
Sure.
I never mind a good troll.
All right. You've probably heard about that in quantum physics. You use just basically everything's a wave.
Yeah. And a particle.
Yeah. Particles, radiations, just fields, forces. You just put everything in waveforms. The interesting thing about it, you can
apply surfboard
display those waves in different ways. for example, let me just get the program. For example, you can basically the same way you do with sound, you can either display the amplitude over time, in which case you're going to get the actual signal that you're sending out. Hold on, let me just set my camera up again. And you probably also heard of something called Fourier analysis or Fourier transformation.
Yeah.
Ever heard of that?
Sure.
Mm-hmm.
Anyone here not heard of that?
I don't think I've heard of it.
I don't even know what you're talking about. I'm thinking about.
All right. You know, in the
Doesn't
old
ring a
days
media
with
bell.
Windows Media Player, there was basically this visualization setting where it would take the tone of whatever you were playing right now, and it
Right.
would do all those fancy things. And there was also this kind of a bar diagram where, and on the left of it, you had the low frequencies, on the right, you had the high frequencies, in the middle, you had the intermediate frequencies, and so on and so forth.
Like bounce up and down. Yeah.
Yeah, exactly. Basically, what this diagram is you're taking the last second of the music that was played and perform a Fourier transformation on it. That's how that works. Basically, you get from the intensity of a signal over time to the intensity of a signal over its frequency. Hold on. Camera back on. So,
the squares.
So you've got the intensity of your signal, and you've got time. And just as a rough example, I'm just going to take a sine wave. That wave has a certain wavelength of lambda, and it's got a frequency which is 1 over lambda. And if I now perform a Fourier transformation of this, where I transform from time into frequency, I'm going to get another graph with the intensity over the frequency, and at that 1 point lambda, which corresponds to the wavelength, or rather that frequency, I'm going to get a rather sharp peak. Hold on, let me just get the program. There it is. And let's give that thing some music to analyze.
I'll be honest, I still don't understand a bit of it.
I think I know where it's going, but I'm not gonna say anything because I'm probably gonna be wrong.
I think you're going to be right. Any wishes for music that I'm supposed to put through an FFT analysis? Rock, metal.
Just do whatever.
Dubstep.
Well, he said
Let's go with
music.
Disturbed.
Yeah.
Yeah, I don't know jack shit.
How do I screen share?
Okay.
I think it's
Wait,
that.
just give me a second.
This one.
No. Yeah, you should see it.
That looks fancy. Kind of looks like the
I think
the
you should hear
graphics
something
from
now.
Yeah, on the roll.
Basically, right now we've got a lot of noise. However, you see some rather sharp lines. Can you see my cursor?
Yeah.
Hold on. Let me go back towards the beginning. Can you see my cursor?
Yeah, we can.
Yeah.
Right here, you hear the rather loud howling of a siren. It's going to silent, so you don't see anything here. Now it's turning louder again. You see the howling again. Basically, that's exactly the frequency. And let me pause that. This is the basically original frequency, and this is exactly double the frequency. That happens when you don't have an exact sine curve, but it's kind of deformed. It's called Oberton in German. I don't know the exact English word.
Yeah, Overtoner.
Yeah.
Okay. Another thing the English adapted. And you basically see here double the frequency, triple the frequency, 4 times the frequency, and here very, very dark 5 times the frequency. Now, when you go on and I'm just gonna unpause this. It's going down because there's no sound, and I continue. Basically, all that background noise turns down to just basically all of this. You see some other, and
Yeah,
yeah,
some other peaks.
now things go loud. I'll just turn it down. And another thing, these vertical thingies here are basically the times when the drummer hits the bass drum. This is where this is basically a double hit on the bass drum, then a short break, another double hit on the bass drum, another break, another double hit on the bass drum, and so on. Hold on, I think that a piece of music might not be as well used to describe that.
Before you go on, I have to go. I have a raiding night with the guild I'm in. So talk to you guys later. I might be back later.
See you.
Bye. Anyway, this is a really fascinating thing that you can play around with. Hold on, let me just find the music file.
And I'm almost done with the horse. God damn it.
Wait, you're actually making it?
Yeah.
Basically, the clearer a tone is, the closer to a sine frequency, to a pure sine, the better it is for, the easier it is for the FFT analysis to just clearly identify the tone. And instead of the white lines you see here, where this is basically the bass player just keeping a either it's the bass player keeping a just constant hum, or it's some kind of the eigenfrequency of the drum set. Now, this is another piece of music I've got on. You see a lot of vertical lines in this. Basically, every single vertical line is one of the sine frequencies identified that you can attribute to a single instrument. Here you see the bass player rather clearly. Lower tone, another lower tone, again going a little bit lower, and now he's playing the tone a bit higher again. And it's getting interesting towards the end of the song. Just let me skip ahead. You still have a significant amount of background noise here, basically because there's a lot of things going on. Come on, when's the end? And yeah, basically now the drummer is going roughshod on the bass drum.
Yeah, that's it's basically just a solid green line.
And now, please be silent and listen closely. And take a close look at these small little lines. You're able to perfectly match them to every single tone that you hear.
Yeah, because they're so clear.
Exactly.
They're like little shooting stars.
Yeah, and basically the reason why they kind of look like shooting stars with at the front they're brighter and they grow darker towards the end is because the Fourier analysis of the fast Fourier transformation, which is also the name on the top left in that image here, is you basically don't a real Fourier transformation doesn't change over time. You take a whole. It's like the graph that I pointed. You get a graph in, and it's going to put a graph out. In order for it to just take a look at the frequency at one specific place or time in the piece of music, you have to cut out a certain piece. However, in a mathematical sense, the Fourier transformation looks like this. Basically, you have an...
You're still screen sharing if you're trying to show something on the paper.
All right. Basically, you've got a signal, and you want to know the frequency. That is the integral from -infinite to infinite of the signal of the space, e to the power of I omega x, dx. That's the thing that you do if you want. That's and instead of from minus infinite to infinite, the program basically chooses basically from now to 1 second ago. And what it does here is it's kind of trying to match a sine curve to the signal that you're getting in, and the more it matches, the more of a result you get for your frequency that exceeds the frequency of the sine curve.
Okay.
Now, in quantum mechanics, you can also basically, if you've got a stream of particles, then the image of that stream of particles, or the wave function for that, is going to look like this. Perfect sine curve. And in order to get from there to the imaging in momentum space, where you're getting the intensity of your stream of particles over the momentum p, it's the exact same mathematical operation. So you again have your wavelength here, and corresponding to that wavelength is to the characteristic wavelength is a characteristic momentum, which if it were here, you were to get a super sharp peak out of that. Just like when you analyze a sine curve. Now, here, our particles are all over the place. It's continuing further in this direction. So if you want to know, hey, where's our particle? In essence, what we're doing is we're taking the absolute square of that. I'm just going to use a different color, which is going to look like this. That's the real part. And there's also an imaginary part to it. So if we want to measure where our particle is, we can basically measure it everywhere. We can also measure it in here, because basically what the probability to measure a particle in a certain area is the integral over the height of this wave function plus this, the second derivative, which means that for c squared of this, you just get this. And in order to find out how likely it is to, let's say, measure a particle in this area, you take, in this range of space, you take the area that's covered, that's in between those two lines, the x-axis and your psi squared, and divide that by the whole area covered under that. So basically the relative area under here is equivalent to the probability to measure a particle in that space. So if you now go to the Fourier transformation of that in impulse space, you get that exact sharp peak. So if you want to take a look at whether the particle is here, the probability to measure it in here is zero. To measure it with a momentum somewhere between here and here is zero, because there's no area covered between your Fourier transformation and your x-axis. If you want to measure it in here, it's also zero. However, if the momentum interval that you want to measure your particle in includes that peak, you get a probability of 100%. Ladies and gentlemen, I present to you the uncertainty relation. Very accurate momentum, very inaccurate place. That's how all this works.
That's neat. Okay, you weren't going where I thought you were going then.
Where did you think was I going?
I thought that that basically that you were going to explain that the peaks that you got from showing the music, that those peaks were what like the peaks in the like more simplified stylized like visualizer were.
Ah, okay. So basically, I've gone a little bit further than what you were expecting.
Yeah.
Kinda.
Just a little, tiny little.
Yeah. Playing around with music and imaging things and separating it in frequency and bam, quantum mechanics.
But you see, all of this is irrelevant because this is based on math, and we all know that math doesn't
No,
prove
you are
anything.
not going to start with that.
Yeah, it's really annoying that Anthony doesn't seem to understand the link between mathematics and physics. Like
Well,
he thinks okay, there's this mathematic formula that works, but you can't tie it to reality for some reason.
I don't
Yeah.
think he understands the concept that, like, pretty much the only way you can prove something is through mathematics.
Yes.
Like that's the entire concept of math is based around the fact that you can objectively prove something.
Hmm.
So
Oh, and just before we forget it, it also works the other way around. So if I give my Fourier transformation an ultra short peak, which would basically be just like a very short bang as a sound, it would give me frequencies everywhere. So basically, if I have a sharp peak on the left and Fourier transform that again, I'm going to get a just flat line on the right. That's also the reason why basically drums, or rather sharp-sounding drums, will just make the entire FFT analysis make a small jump. And that's basically because why all those horizontal lines were the drum sets. Drawing the connection between music and quantum mechanics. I love physics. You can overload everything with theory.
and while you did that, all I did was make a horse.
But not just any horse. A horse in IKEA. It's
That was
IKEA's new mascot.
Sorry, sometimes I just need to geek out.
Well, I can see you wanted to actually talk about more high level and more interesting physics, considering that you've basically been doing high school physics, so trying to teach that to a grown man.
Well, is it even high school level?
Hold on.
I think I learned it in the equivalent
let me
of
show
high
you
school.
something.
Well, I mean, so okay, so just because it's fresh in our mind on the pyramid hangout thing, when he talked about the missing dollar problem,
that was the first homework of this semester's quantum mechanics lecture, and that's only part of it. Hold on, let me just
Jeez.
zoom out a bit.
Dear God. See, this is why this is one of the things I prefer with biology. The math is never really that complicated, because as soon as it gets complicated, you can basically just assume that it's too complicated. We don't have to take it into account. Like nothing is on. There's so much, especially like in ecology, there's so much uncertainty in everything. Like all variables are like, it's around this.
Yeah. Also, guys, fun fact: this entire page is only the first half of that calculation.
Well, we all know that the answer is 42 at the end of the calculation anyway, so I don't see why you bother doing it.
Nope, not exactly. The answer is a index n plus 2 equals 2n plus epsilon minus 1 divided by n plus 2 times n plus 1 times an. It's basically a recursive condition for the indices of the
Then you did something wrong. It's supposed to be 42.
Taylor expansion.
Yeah, it is.
Of
42.
the radial part of the wave function of an electron inside a hydrogen atom.
What he
Too much
said.
math? basically, we were calculating how the wave function for an electron looks like inside a hydrogen atom. And in order to do that, we used a polynomial function as a ansatz, and these are the coefficients these are the single coefficients inside that wave function.
Hey, Hector, was the electron positive?
Oh no.
What do you mean?
Yeah, during the pyramid debate, for some reason, Anthony suddenly talked about positive electrons.
Oh yeah.
Positrons.
Yeah.
Fun fact: the last lab course experiment I had was examining data from the LEP back when they didn't have the Large Hadron Collider at the CERN, but the Large Electron Positron Collider, where basically they created Z0 bosons that decayed into all kinds of weird stuff like quark-antiquark pairs, lepton anti-lepton pairs, and we just analyzed everything. And every single time, we didn't only have scattering events, we had both scattering and annihilation events. So basically, electrons and positrons kind of doing stuff, but not annihilating, just being ricocheted out of the acceleration line into the detector. And we had events where they actually annihilated, created a Z0 boson, and that then again decayed into electrons and positrons. And telling those two things apart was such a fucking nightmare.
So, okay. So for someone that is, at least in this field, it's okay, a layperson, not even, right? So the detectors in the particle colliders, I've never actually read anything about how they actually function. Is there any way of like describing that in short, like how you can actually detect the difference between?
Have you ever heard of the term Cherenkov radiation?
Oh,
I've heard of the term, yeah.
Yep.
It's basically if you have a particle that for some reason has gotten a shitload of butt kicking and is flying through something at incredible speeds, then it's basically like a car driving past you with 300 miles an hour. Just the drag alone is going to make you stumble. And in the same way, an electron, for a charged particle flying past anything at ridiculous speeds, is just going to give that other thing a little bit of a nudge. And that nudge is usually enough to excite atoms or molecules to the point where, when going back to the de-excited state, they emit a small photon. And basically all that most particle detectors work on just looking at a block of glass or something else that's packed with something that's not going to let light come in, and wait for a little flash of light.
So it's essentially an extreme level of spectroscopy. Just put it plainly. Like just very, very simplified.
It's
obviously.
more like looking for the light equivalent of sonic booms.
Yeah, kind of. The light equivalent of sonic booms is something a little bit different.
Yeah, that's something else they've actually discovered or filmed or whatever recently.
However, let me think about it. No, what I was talking to you about isn't called Cherenkov radiation. Cherenkov radiation is something different. But basically, I think those are scattering events due to Bremsstrahlung or braking radiation. Basically,
you're talking about Bremsstrahlung. Okay.
Exactly. Cherenkov radiation is kind of literally sonic booms with light.
Yeah, that's why I've said
what
it.
exactly the refractive index of a medium means. Basically, the speed of light that we talk about, 300,000 something kilometers per second, that's the speed of light in vacuum. And the reason why it's emphasized that this is the speed of light in vacuum is that in other materials like air, glass, diamond, and such, the speed of light is actually lower. And in essence, if you multiply the speed of light inside a medium with the refractive index of that medium, you're going to get the speed of light in vacuum. So if you divide the vacuum speed of light by the refractive index of a medium, you're going to get the speed of light inside at which light propagates inside that medium. And basically, that effect is also how refraction works, how lenses works.
Yes.
Interesting stuff, but for that, we're going to need wave mechanics, and that's nothing for today. However, basically, that speed of light limitation for just how fast an object can move counts for the speed of light in vacuum. Now, what happens if you've got a medium with a refractive index of 2, which means the light inside there is going to move at half the speed, and you shoot a particle in there that's going 90% of the speed of light?
Yeah, you're gonna end up with, yeah, as I said, basically a sonic boom.
That's exactly the same like a sonic boom.
Yeah.
And that's Cherenkov radiation. That's the blue glow that you all often see from images from nuclear reactors that are running.
Yeah.
There's also detectors.
Isn't that also what they used to look for, like they use in neutrino detectors?
Oh yes, neutrino detectors. Those things are awesome.
Right, yeah, that's right. Yeah.
Super exaggerated. Basically, neutrinos are the smallest things and the lightest particles that you can ever think of. These things are so light and so small that
they have a virtually a 0 chance of interacting with anything.
No, that chance isn't exactly the 0, and that's
but
the fun part.
It's extremely low.
Yeah, when you're talking about collisions between particles, there's something called the interaction cross-section. It's basically how big is the target that you need to hit for something to happen. And for the interaction between neutrinos and basically anything, that interaction section is so incredibly small that the majority of neutrinos that are thrown at the Earth from either the cosmic background radiation or the sun or atmospheric effects, they are so small that they are going to fly straight through the whole freaking Earth.
Yeah.
That's how small these things are. I always use the comparison: they're small enough to fly in between the protons and neutrons of the core of an atom, but given that everything inside there is just a clusterfuck of quantum mechanics and quantum field theories, I'm not going to use that comparison. However, without the neutron actually hitting anything, it's just going to fly through your detector and do nothing. And you're going to need a freaking big detector just to have a chance of just anything happening. I mean, just as a comparison, hold your thumb towards the sun. Just take a wild guess. Per second, just from the sun alone, how many neutrinos are going to fly through your thumbnail?
A lot.
Yeah. Billions? I don't know.
66.5 billion per second per square centimeter. How many neutrinos per year do get stuck inside your whole body?
Maybe 1.
Just about 1 per 5 kilograms of body mass. These things are small as fuck. So,
I gotta say,
what do you
some
do?
very ineffective birdshot.
Kind of. So,
yes,
what
I
do
knew.
you do
I
to
knew.
detect those?
I found it. Haha.
Basically, what the guys at our university did is they took something called a photodetector, which is basically a detector for ultra-high energetic photons. And they can actually measure single photons. We also did a lab course experiment on that one, but that's for another day. And tied them to anchor chains with an anchor at the bottom, the top, and dumped them into the ocean. 2 kilometers long, about 30 detectors on each, and left at the bottom of the ocean. They hooked them up to kind of a underwater server to pre-filter all the data to get rid of any noise, and then reroute the data back to the shore. In essence, they've installed a wiretap on 3 cubic kilometers of seawater. And each year, inside those 3 cubic kilometers of seawater, they're getting about 10,000 neutrino events that they detect.
Nice.
in essence, what they're waiting for is for one of the neutrinos to just smash into stuff, and in the process, it's going to create a lepton. Basically, an electron neutrino is going to create an electron, a muon neutrino is going to create a muon, and a tauon neutrino is going to create a tauon. And those are elementary particles that you can rather clearly see. And as most neutrinos have just a shit ton of energy to them, they're going to create Cherenkov radiation inside that neutrino detector.
Mm.
And that's something that those photo detectors are going to notice just as a big, small flash. Now, fun fact about the detectors, something that's going to be interesting to the biologists. That detector isn't in a just enclosed system. I mean, yes, it's 3 kilometers under the surface of the ocean. There's not really a lot of light coming from the sun down there. However, there's microbiologic life down there. And those little thingies, it also communicate via light.
Well, not really communicate, more that it's a way of startling predators and attracting prey.
Whatever they do, they're glowing. And basically...
and it's blue, usually.
I've got no idea about that one, but anyway, since the light they emit has a rather lower wavelength, it's rather easy to filter it out. However, every year in spring, when all the snow starts to melt and go through the rivers, it's going to flush out a shit ton of nutrients into the sea, also from a river close to the shore station, which means that there's a lot of cold water from all the ice that has melted, a lot of nutrient-rich water collecting on the surface of the ocean, until at one time they wait for a school of fish to take a rather hard dive or whatever. Which means that all that cold water is going to start just plummeting down towards the bottom of the ocean, and just give all those microbiological organisms a massive shot of nutrients, which is means there's a fucking laser party going on inside the detector. Which means that every year in summer, a group of biologists comes knocking to the Erlangen Center of Astroparticle Physics and just basically asking for the data trash that we threw out to just use that for their research.
Cool. Did you see the thing I posted in the chat in the hangout?
Yeah, I've been reading it while I'm listening in. I like the a supernova from 1AU or the hydrogen bomb pressed against your fucking eyeball. Which one is brighter?
Yeah.
Oh.
A supernova. By 9 orders of magnitude. Holy shit. So it's not just barely brighter, it's... Yeah. Man,
I like the comparison. What is brighter? The supernova happening at where the sun is right now, or detonating a hydrogen bomb pressed against your eyeball? And yeah, the supernova is a billion times brighter.
Yeah. So you can tell the difference.
No, you can't.
Well,
also, interesting things about supernovas and neutrinos. Basically, when a supernova happens, basically all the big boom causing stuff happens within about 100 microseconds, which is basically when the sun collapses the remaining 90% of its size towards a white dwarf.
It's the single most energetic event in the universe, isn't it?
Exactly. And
I thought that was black holes colliding.
Not all of a star is going to collapse. There's still going to be kind of an outer shell of just stuff. And the thing is, that stuff isn't completely transparent because it's freaking dense. And when a supernova happens, it's not a big flash. A supernova reaches its maximum brightness at between 1 and 2 years after basically the first light from it has arrived. Just because all the light is being scattered and reflected around inside that incredibly large bubble of super compressed matter. It's basically a hollow sphere that's nearly impermeable to light. And as the supernova expands, that outer sphere gets thinned out and leaves more and more light through. Now, something that isn't really permeable to are neutrinos, because remember, those things go through everything. So, when the guys in the neutrino detectors notice, oh, holy shit, we had about 5 events at the same time. Wait, where did they come from? Turn your telescopes that way, and then say, all right, I think we're going to see a supernova there. It's basically a, hey, watch out, there's something interesting going to happen from the universe.
Okay. I think I'm going to end the sending out now. It's been...
Come on, already.
Wait, it's still going? I
Yeah,
thought you'd turned it off.
No, it's still going.
I mean,
I figured if something interesting might happen, there's no use cutting it out, but I think, yeah, we'll stop it now. So bye.
Come